The restrooms for this building are straight out the doors, all the way to the side. Sorry, Angela, by the elevators. So there are a men's restroom, women's restroom, and there is a single stall restroom as well. So without further ado, we are going to kick. Oh, sorry, Angela has something to say as well.
So we are going to be joined for lunch by the faculty, and the faculty will intermingle with you all. I guess we're having lunch out. Are we having lunch out there?
No.
We're having lunch in here. Okay, so we're having lunch in here. So at the time of lunch, we're going to have, we want faculty at each table, so you get to meet them. We don't want all the faculty clustered up front. So be mindful of that. Some of you might want to, switch it up where you're at during lunch so that you can interact with the faculty that are here for lunch with you. Thanks and welcome everybody. We're glad to have you here.
Great. So we're going to kick it off with our chair, Professor Steve Wright. Thank you. Welcome.
Okay, welcome everyone. This is my first time doing this. I just became chair 8 months ago, so I'm still learning the ropes. So cut me some slack if I mess things up. So first of all, I want to thank Molly and Angela for all the work, and Kyle is also there, Kyle Martinez, who directs our professional program. I want to thank them for all the work they've done in the process of organizing the applications and serving on the committee that selected you to come or to receive an offer. And I want to also congratulate you all because fewer than 10% of people that applied got an offer. And of course, we wish we could offer more places, but our building is limited in space and our professors are limited in bandwidth. So we have to be somewhat selective, and you made the cut. So congratulations on that. Okay, it works. Great. Okay, so I'm going to maybe just give you a little bit of a sales pitch about Madison and about our particular department. So the first question that I think you probably asked yourself already, but I'll ask it again, is why would you want to come to Madison? And I think the first thing is the place. So Madison is spectacular. Maybe today's not one of our greatest days, but if you're here in the summer and you're up in the plane flying into the airport or up in a helicopter, you'll see a view like this, which is you can see the state capitol right in the middle there between the two lakes. The university is down around about here, I guess. It's hard to make out from the rest of it. And this is the isthmus. You'll become familiar with that term isthmus if you didn't already learn it in high school geography. This is Picnic Point. All of you at some point in your career here will take a hike out to the end of Picnic Point. It's nice. It's a nice walk from our department to the end of Picnic Point. How long would that take? Maybe about 35 minutes, maybe walk. Anyways, a lot of exploring to be done. I learned to sail 3 years ago. There's a sailing club right here on the lakeshore, right under the Memorial Union Terrace. And so if you join the sailing club, you can take sailboats out onto the lake. Fantastic thing to do. I recommend looking into that. If you're a student, you pay much less than I do. You really get a tremendous deal. And even if you don't think you're interested, give it a shot. There's also a kayaking club there, which is a little bit less adventurous, but you can, on days that aren't so windy, you can kayak over to Picnic Point from the Union. That's a fun thing to do. Anyway, so summer's great. Madison makes #1 in a lot of best places to live ratings, certainly near the top very often. And now the winter is milder. It used to be that when we'd have visit day, we'd still have snow on the ground and all that stuff. This winter, I've been in Madison 24 years. It's by far the warmest winter since I moved here. There was maybe 2 periods when it got genuinely cold, and the rest of the time it's been very moderate. This week has actually been spectacular. This is the first rainy day, but it was sunny and cloudless and warm the first few days of this week. And the summer, even if the winter is bad and even if it gets you down a little bit, you can look forward to the summer, which really is amazing. It's very moderate temperatures and just generally spectacular weather and a whole lot of things to do. This is I think this goes way back from a magazine back in the 30s or 40s. And you can still see scenes like that. Maybe people are dressed a little differently these days, but certainly the scenery is very similar to there. And physically, this is what it looks like looking down from above. So you'll recognize the isthmus there. The Capitol is there in the middle of the square, and then the university is, basically it's this area here. This is Picnic Point here. Okay, so, and that's what it looks like in the fall for a couple of weeks when the leaves fall. Okay, so a little bit about history. So our department was the second CS department in the country. It's founded in 1964. And like many computer science departments, it was an offshoot here of the math department. In some places, an offshoot of electrical engineering. Purdue beat us to the punch by 1 year, but we were the second. And even before our department came along, we had some very famous people from the history of computer science that came through our university. So John Bardeen actually is a native of Madison. He's one of the few people that win the Nobel Prize twice. He won the physics Nobel Prize twice, once for inventing the transistor and once for discovering superconductivity. And he was a native of Madison. He did his undergrad here. Gene Amdahl also he actually did a theoretical physics degree and graduated in 1952. And he told his advisor at some point, okay, for my thesis, I want to make a computer. And so he made a computer called the WISC, W-I-S-C, Wisconsin Integrated Scientific Calculator or something. It was the first digital computer in the state of Wisconsin. And I'm not sure if it still exists, but there are pictures of it on the web. And of course, it was one of these things that took up most of a room and had vacuum tubes and all that sort of stuff. But he went on, of course, to this amazing career at IBM. He was a designer of the IBM 360 and later the 390. And then he started his own company, Amdahl, and then spent the later part of his life doing a lot of startups and so on. So very, very influential guy in the field of computer science. In our department, in the early days of our department, we had some really foundational people, including Stephen Kleene and Barclay Rosser. And this is a quote from a letter when Alan Turing visited Princeton. He wrote back to his sister about the great mathematicians that he found. And he reels off a list of very famous names, von Neumann, Courant, Hardy, Einstein, and so on. But then in the end, he says, well, there aren't as many people that do logic. But he mentions 5 people, and 2 of them are founding members of our department here. So they were, right from the start, very eminent group of people. And then also, after that first generation, which was basically mathematicians, numerical mathematicians and logic people, they had the foresight to sort of branch out early on into other areas that we now recognize as being areas of modern computer science, like database management systems, computer architecture, the early days of networking and so on. And many of these had very important roots here in our department from early days and continuing through now. So why am I telling you all this? Well, one reason is that the tradition continues today. And you can see imprints of the department from 60 years ago. This is our 60th anniversary, I guess, in the makeup of the current faculty and the things that we work on. There's one more thing I wanted to mention. Yeah, the first PhD, we produced either the first or the tie for the first PhD in computer science in the US. And you'll probably hear the name again today. This is Sister Mary Kenneth Keller. And she was a nun, and she wrote her thesis in 1965. And we know the day that she graduated. And it turns out that Purdue also graduated a PhD student the same day. But we're not sure of the time of day. So we're not sure whether it's first or second or it was the same moment. But certainly it was right up there. Okay, so in research, we do a lot of different stuff. In fact, I've got it on the next slide, sort of areas that we're well known for. Databases is a big thing here, programming languages. We've got great systems people, some pioneering people in architecture, great people, younger people in visualization. I would say machine learning, of course, very hot area that I know a lot of you are interested in, computer vision, HCI, and so on. These are just some of the awards that we've got in terms of funding over the last 12 months, so that we've had 40 projects funded. It's almost 1 per week, and $10 million in funding. And I've just written down a random subset here of members of our faculty that have got outside funding. And this matters to you because if you become an RA for a professor, that your RA research assistantship is going to be paid for typically out of one of these grants. And so funding, you'll care about funding. And in fact, many of you during your career will help to prepare proposals for funding. Okay, so what about education? Well, we think we have a great curriculum. Of course, it keeps developing as the field changes. We keep adding courses to the curriculum, maybe dropping some that are of less interest anymore. Every university has its own way of coding courses. Our undergrad courses are coded up to 600 level. 600 tend to be the more advanced ones. 500 level are typically things you take in the 3rd and 4th year of an undergrad degree. When you get to grad school, you start taking classes at 700 level and higher. Now, many of you will also take some 500 courses. You're allowed to take a certain fraction of those as part of your degree if you want to fill in some background in certain areas. The 500 courses I teach tend to have about a quarter to a third of the class being grad students. And these are some books that our faculty have written. I was shameless enough to put up one of my own books here. Our former chair, Ramzi Apache-Dussault, and his partner, Andrea, have this very well-known book in operating systems. And this is just a sample of some of the books that we produce that sort of are relevant to education. Okay, so what about people? So you'll want to know about the professors here and the other students and the staff. And I would claim we have really terrific people here. And what's the evidence of that? Well, I can point to awards that people have won just in the last year or so. I've got a list here of recently our colleague Zhang Yao Yu won a Sloan Fellowship, very prestigious award for young researchers. And then I have a list of assistant professors who've won what's called Career or Young Investigator Awards. And these are very prestigious awards that go to younger people at the start of their career to help them get launched in research and also in teaching and education. That's an important part of it. Our colleague Sharon Lee won from MIT Review magazine, a very influential magazine in the tech area. She won the Innovator of the Year award last year. Karu, our colleague Karu, is a computer architecture guy, became an IEEE fellow. Several of our colleagues won internal campus awards. The campus makes awards across campus of distinguished professorships and research professorships. And 2 of our colleagues were awarded those recently. And then there's a couple of others at the bottom that I won't mention. So here is some pictures from our website of our faculty. And I think it's alphabetical order. So you'll see Ramzi, our former chair, and Andrea up here, up the front, because their name starts with A. And I'm down here in a very outdated picture from 12 years ago. So I'm sorry, it's a little bit of false advertising there. And then we've got some colleagues whose names start with Y and Z. So they're unfortunately at the end there. But we have a great roster of faculty. And also staff. You've interacted with some of the staff already. Angela and Molly were just up here a moment ago. Cindy is our administrator for academic services, and she's got her back to us right now. No, she just turned around. So there's Cindy over there by the coffee. So she's tremendous. I work with Cindy a lot. She's a tremendous member of our faculty. Kyle, I introduced earlier. He's standing at the door. You probably met him when you were checking in. We have a computer systems lab that you'll be interacting with if you want to do anything involving a laptop or getting set up on the internet or getting your mail set up, or possibly in the course of a research project. Nibadita, I don't think is here, but she's another person in our graduate program. And then Hillary, I know a lot of you are getting some financial support to come here, and so you'll be interacting with our travel people, and Hillary is one of those to get reimbursed. Okay, many students, but let me show you some former students. And there are many distinguished former students who have gone on to great careers in academia and industry. And Andrea, you're telling me to get off? Yeah. Okay, wrap it up. Okay, that means get off. All right. So I don't have too far to go. Okay, so Sarita is a colleague. I think she graduated in the late 90s, and she's at Illinois now. Joe Hellerstein, very distinguished person at Berkeley. He was a graduate of our data science group. Judy Faulkner is the founder of Epic Systems, which is the biggest employer in this area, medical informatics company. And Colin was a student 20 years ago in the master's program, and he founded a company called Pinduoduo, which is now China's biggest e-commerce company. Overtook Alibaba recently. Yeah, he was a graduate of the database group. Okay, a little bit about the school. We organized with the statistics department and the info sciences department into a grouping called the School of CDIS, Computing, Data and Information Sciences. This has been running for about 5 years now with the founding director, Tom Erickson. And it sort of, it recognizes that in the way that research has evolved, there's a lot of common interest between these departments with the whole AI and machine learning thing that sort of brings together CS and stats. And also the iSchool brings in sort of the human aspect of that. And one of the outstanding physical manifestations of this grouping is this new building, which is right next door. So you'll see it, you probably saw it on the way in. This is what it's going to look like in about 14 months' time when it's all landscaped and everything. That's the view from University Avenue. That's what it'll look like when you're walking down from the Student Union towards here. This is what it looked like in June last year. So this is only, less than 9 months ago when they'd done the groundbreaking and got the first 2 floors up. This is what it looked like yesterday when I took a picture out my office window. Almost all the external floors, external framework is done. There's 1 more floor to be added, I believe. So this is 3, 4, 5, 6. No, I guess that's the top floor. So they just have to sort of put a roof on that and we're done. And then it'll take about another year to fill out the inside. But a year from now, after you finish your first year of study, this will be moving in. And so you'll spend a lot of time in here. This is what the big classroom will look like. It's got a lot of teaching space in there. You'll spend a lot of time hanging out in that building. It's got an atrium that goes all the way up to the top. It's called the heart of the building, I guess. So very spectacular interior. And just to summarize, many reasons you should come here. To sum up my talk, there's place, there's history, research, great research, education, great people. It's a great school. And there's the spectacular architecture of the new building. I couldn't really figure out how to make a acronym out of that, but then I just rearranged them and, oh, hold on. Oh, I messed up. If you rearrange them, you get the word perhaps, okay? And unfortunately, I left that slide off or cut it out at the last minute. So anyway, so the punchline completely fell flat. So thank you for that. And so enjoy your weekend. Have a great day. Have a great time tomorrow. And I will be here at lunch. I'll be here at dinner. And I look forward to interacting with you then. Thank you very much.
Hi, good morning. Let's, I guess the slides will come up. So my name is Josiah Hanna. I'm a professor, I'm an assistant professor. I'm in my 3rd year here, and I'm going to be joined on stage by a robot dog. So I'm representing the robotics group here. So we thought we'd, this is a robot from my colleague Mike Gleischer's lab, and they're going to do a bit of a demo later after I talk a bit about the group and the work which is being done here. So before I get into my presentation, let me just add my congratulations on your acceptance. You know, it's I'm on the admissions committee. It's a very competitive process. It was very hard decisions that we had to make. So, you know, you should feel very, very honored. And I hope you come here. It's a really exciting time for you. Graduate school was some of just incredible years. And, you know, I'm excited for everything that you have ahead of you. And I hope you spend those years here. So robotics research. So these are the robotics faculty here. So we have 5 members of the robotics group. So I'm gonna mainly talk about research from my colleague Bill Gay, my colleague Mike, and my own work. Mohit and Youngjae, I think you're gonna hear a bit more about their work. They kind of sit between the computer vision group and the robotics group here. But okay. So when you look at like a robot like this, basically robotics research in CS is like, you know, what is like the software which powers robots, which are going to enable them to do kind of all sorts of interesting things in the world. So you look at a robot like this and you think like, okay, well, what does this robot need if we're going to have it, you know, just maybe wandering around this building, helping people do different tasks? And I think one of the kind of key things that you need a robot like that to do is to be able to interact with people. And so this is really my colleague Bill Gay. His lab focuses on human-robot interaction. So this is the People and Robots Laboratory. So to just show some, you know, kind of examples of things that you might want to do with robots is how can how can you efficiently control a robot if you're a person? Like, you want to get a robot to do something. People have a lot of knowledge, but the robot is a very different kind of embodiment. So how does a person efficiently control them? So this is just one example of their work, showing some mimicry control where the person is able to move their arm and the robot is able to copy the movement. And this gives the person a really easy way of controlling the robot, because they can just kind of move in what's like a natural way for them. Some more, this is kind of some more work there, doing this with like 2 hands now. So you have a person who's demonstrating like how to make something in the kitchen, and then, well, the other video is not loading, but a robot can do it as well. Another key thing, which is they've looked at, is like, how can robots help people kind of better themselves? So, for instance, one possible use of robots is like companions for promoting learning in students, like particularly like students who may be like isolated as they're trying to learn. For instance, a skill like reading, where you've got to spend a lot of time by yourself, and you might need some encouragement to like keep trying if it's difficult for you initially. So this is some work where they actually tried, like, how does a person respond when you have a robot present with them, helping them with their schoolwork? Okay, go over that quick. So the next person I want to talk about is my colleague, Mike Gleischer. So Mike's research is, Mike works in a lot of different areas, but he's done work in graphics, and more recently he's been doing a lot of work with robot interaction. Like, how can people understand what robots are doing? So visualizing their behavior, as well as how robots can kind of control themselves to do all sorts of really complex tasks. For instance, visualization of robots. So how can you like show a person what is a robot doing, and do this in a way which is like interpretable and allows the person to understand, how to intervene or provide information to the robot. Right. So you want people to be able to easily specify to the robot what its goals should be, and to do this in a natural way for people. You want people to be able to control robot motions, specify what desired motions are, and then interpret what the robot's doing. It's like, even if a robot can solve a task, it may not necessarily be clear to a person that the task is getting done. For instance, if you've seen a robot vacuum cleaner, at some time it just wanders around randomly. This is kind of the initial implementation of Roomba. How can you be confident that your floor is actually being cleaned? On the other hand, if you see a robot that's going kind of like back and forth in this like lawnmower pattern, you can be more confident that the robot is actually covering everything. From a functional viewpoint, moving randomly is just as effective as the lawnmower path, but one is much more interpretable to people. So yeah, more work there. Providing viewpoints to people. So in this work, the question is, if a person is controlling a robot, how can another robot kind of provide the most informative viewpoint for the person to observe the robot and decide how to control it? So this is an example where maybe you have a robot which is, it's in some remote location and you want a human to operate it. But if the human can't see the environment correctly, you need to kind of be, how does it know exactly how to move the robot? So, and this is work of like using another robot to provide visualization in the case. Okay, yeah. So now another project which has come up in this lab. So this is again still Mike's work, is when you're like wanting to inspect like a really large truck where you don't know like the environment initially. This is kind of motivated by some applications of storing nuclear waste. So say we have this truck and we'd like to know if it's been contaminated with some nuclear waste. You might want to send in a robot to sweep the truck. So this is actually what the purpose of this robot is to be able to send it into these kind of toxic environments where you don't want to put a person because it could be dangerous, and you want them to confirm whether or not there's something that could be harmful in the environment. So again, you still have these kind of questions about like, how do you know that the robot has done a good job? How can you enable the robot to do a good job, like giving it the proper control to go into such an environment? And so that's what the purpose of this robot is for these tasks. But then and you'll see a demo at the end of the presentation today, but there's a lot of really interesting research questions which come up in this work. So specifying objectives to the robot is always kind of a key problem. How do we give the robot good motion plans? How can it come up with automatically what a good motion plan is to accomplish its task? How do we know that it's a good plan, verifying that it's doing a good job? How do we monitor it to ensure that it's doing a good job? And then once it's done, how can we confirm that it's done a good job? So these are all some like research questions, which are really hard for today's robots, and Mike's lab is tackling this in this platform here. So now to my research. So what I'm generally interested in is intelligent agents which learn how to act through experience. So there's many different methods for programming robots to do a fixed thing well, but the world is such a complex place. It's like such a dynamic place. The world today is not the world that will be there tomorrow. So if you just program a robot in like a fixed way under some like fixed algorithms to do something, it's probably not going to work tomorrow. You're gonna have to reprogram it. And this is, I mean, if you see like, we don't have robots which just like are interacting like in the natural world. They're usually confined to labs and factory floors. So I think learning is key to being able to like scale robot systems to the complexity of the world. Learning is a key part of why, you're a functional agent who can like interact in like the natural world. So my lab focuses on reinforcement learning as the key technique for doing this. Reinforcement learning is the branch of machine learning which focuses on learning goal-driven behaviors from experience. Basically, that kind of the idea here is just impossible to program the right action in every given situation. We want agents that through their experience over time get better and better at learning. One of the kind of key areas where my lab has been doing research is on the testbed of robot soccer. So robot soccer is a very complex, if you just think about like playing soccer, if you've played it yourself, it's actually, when you try to break down everything that you have to do, it's like a really challenging task for any robot. You've got to reason about like a lot of like different people, different agents. You've got to reason about your teammates, your adversaries. Most of the time, you can't even see the full view of the field, so it's very partially observable. What I'm showing here is work we've done on trying to just enable robots to move better. So in particular, we do work on like using simulators where the robot learns in simulation. And we can take small amounts of real world data and use it to make simulators more accurately represent the real world. And then our robots can learn in simulation and they can get much better at learning to walk or to do other sorts of skills. This was work that I did a while ago where we ended up making a robot walk faster than anyone had been able to program it before by using reinforcement learning as opposed to more like manual, like classical control methods. More recently, we've been taking a thrust of doing more learning multi-agent behaviors here. So I'll just show some quick videos, but this is where we have a really like very low fidelity simulation of the world, kind of in the way that when, if you imagine the way you think about the world is often at a more abstract level of imagination, not like very high fidelity. And so we learn in this abstract representation of the world, and then we're able to transfer the behaviors onto physical robots. So this is my lab across the street in the computer science building. And so this is what that we're able to make these robots performant when we deploy them. I'll just like add really quick. So reinforcement learning is a fairly general paradigm. So my lab does work outside of robotics as well. I'm just trying to make optimal decision makers who learn from experience. Okay, one slide. You'll hear a bit more about Yongjae later, but Yongjae's main research is just creating AI systems that understand visual data as well as being able to generate kind of new images, as well as having multimodal vision and language understanding. I think you're going to hear more about him later, so be a bit quicker. And then the Vision Lab, which is led by Mohit Gupta, also in computer vision, does a lot of work with unconventional cameras. So both like kind of developing the hardware, like fundamentally new types of sensing that enable us to make sense of the world in a different way than just the kind of cameras that you might have on your phone, as well as developing the algorithms which enable us to use that data. Just going to briefly plug this program which started. This is a NSF traineeship program, Integrate, which was founded by a number of faculty here. It's funded through NSF. You can get involved. It's a great way of doing interdisciplinary robotics research, being exposed to much more than just the computer science side. And then lastly, I'll just add that there's a lot of robotics happening at Wisconsin-Madison. So there's 5 of us in computer science, but we also collaborate with people in mechanical engineering and civil engineering. And those people, like, they really want to learn about the computer science side. So it's worth, if you're interested in robotics, it's worth looking into, the research in other departments as well. So with that, I'm going to actually let some students from Mike's group come over, and they're just going to show some of the capabilities of this robot. But with that, I just want to add congrats again on your acceptance, and I hope you come to Madison.
Hello, everybody. Good morning. I guess I will also triple congratulations on getting into UW. So we're just going to show you a quick little demo here of our little Spot robot from Boston Dynamics. He'll come over and we'll pick up this block off the cone autonomously. Cool. So some fun facts about Spot. He weighs 90 pounds. So fun of a fact. He's got a couple depth sensors. That's how he sees. Oh, look at that. Good boy. So he's got a couple depth sensor cameras all around that help him see and avoid object collision. So you can even attempt to walk him into objects, but he won't actually typically walk into objects he'll collide with. And anyway, do we have, you can kick him and he'll self-balance. We won't kick him because that's mean, A, but also he'll fall off the stage and that's not ideal. And he can obviously climb up slopes and stairs, which is kind of hard. I think that's easy to imagine why. Yeah. Anything else that we wanted to cover? I think that's it. Oh yeah, right. We're going in chicken mode. So he can keep his gripper in stationary within the world. And actually, if you'll notice, sometimes he's walking so that his hand actually can't still be in that same space. But once the gripper can be in that same space, it remembers where it was in the world and keeps the gripper there, that little end connector. So yeah, Spot's very cool. We're very excited to have him. I think that's it for us. Yeah.
Good morning for the 10th time today. So a disclaimer, I don't have a robot, but I have slides. And I have this, which I will explain later. Okay, my name is Qasim. Hi. I'm an associate professor here in the ECE department, actually, but I have an affiliate position in the CS department, just to let you know how our departments are very collaborative. I'll be talking for the next 8 to 10 minutes about the security and privacy research at UW-Madison. And my intention is to get you back on schedule. Cool? Okay. You all heard about technology, right? Cool. Who uses a smartphone, by the way? Who uses ChatGPT? Who uses ChatGPT in coursework? How do I use ChatGPT in coursework? I have it design my own assignments now. Cool. So technology is reshaping our lives and society, and that's a statement that's always going to be there, right? New technology, new shaping forms. And then securing our data and infrastructure becomes very important. And I'm going to give you some examples of this. And these examples will include robots. So security research involves understanding and improving the behavior of our technologies in the presence of adversaries. And adversaries are put here in red. So let's take an example of an old technology, machine learning. How old is machine learning? It's like 2 years old. Now it's all AI, right? We don't use ML anymore. It's all AI. So in the old days, like 2 years ago, ML used to achieve lots of interesting things. It could recognize things from images. It could do face recognition. I wouldn't say beating doctors, but it could do some stuff in radiology, in medical imaging and analysis, CAPTCHAs. And it can do lots of things now, as you know, in ChatGPT, large language models, vision language models, and all of these things. But the interesting thing about these models, when we design them, we're always optimizing for what? Performance, right? Josiah said performant. He didn't say secure, right? So they only assume there are good people in the world, which, as we know, is not entirely true. So I'll give you a very classical example, and I'm pretty sure many of you have seen this thing before. What's this? Cat. What's this? Guac. It's not cat anymore, right? Why? Because the models that analyze these images do not perceive the world the same way as humans do. And that means that you can inject some structured noise, or you can modify this picture or this image in some way, and then you can trick the model. And now you can imagine how this thing can have repercussions on our systems. So let's take examples, a malware detector. Machine learning is used to do malware detection, it's used to do spam detection, right? But then as an adversary, you want to trick it. I want to modify the input so that the output is different. Or speech recognition, or other examples. And I will show other examples from our research as well. And the big problem here is that machine learning is being and is going to use in very safety critical systems. So there are robots, there's autonomous vehicles, and then there's a question. How much do these systems understand? What do they see and what do they hear? And then see, hear, and understand are between quotations. Because we think they understand, we think they see, we think they hear, but we don't really understand how do they understand. We don't really understand how do they see or how do they hear. And that results in lots of security and interesting security and privacy problems. Now, interesting from my perspective, not interesting from the world's perspective. And one of the problems is cars and robots' understanding of the world is a bit shallow, despite them using very deep neural networks. Why? Because these systems rely on sensors, right? Josiah told you about sensors. So sensors give you what? Give you raw data. How do you reason about this raw data? You need some sort of machine learning classifier or an AI model now to reason about this sensory data. For example, you have an image, you need to do object recognition to see what is there in this image. Or you get depth data you need to analyze. But then people have shown that you can add some stickers on a stop sign, and then you can trick this classifier. So I'll show you an example, and hopefully it works. Okay, so what do we have here? We have a normal stop sign. The model says stop, right? We're gonna go back. We have a modified stop sign. The model says speed limit. Now imagine this is an autonomous driving vehicle. What would the vehicle do? It won't stop, it will just go. And we know there's some very famous brand in the market that have made the decision they only want to use cameras. You know that company? Yes. Okay. Of course, there are problems here. And the problems are not just in the vision domain. I'll give you an example in the voice speaker identification domain, and that's part of my research. You've heard about voice prints, right? You talk, then there's a unique signature of your voice. You use that to authenticate people. But can we trick those? Of course you can trick those. You can replace someone's voice. You can clone their voice. But we had a question. Can we do that without any digital manipulation, without using a deep neural network? Can we impersonate someone in the eyes of a system, or actually in the ears of a system? It turns out we can. And you just have to use what? A tube. Why? I'll demonstrate very quickly. Hi. Hi. My voice changed, right? Why? Because a tube has a resonance effect, and it reshapes your frequency spectrum. When you reshape your frequency spectrum, that means that the input going to the model has changed. And you know that these models are finicky, so the model output changes, then you can impersonate people. So I'll spare you the technical details, and this is where ECE and CS start intersecting. But to spend a lot of time to actually get the theoretical model of a tube matching the real world model of a tube. And for a while, we had like few hertz discrepancy, and turns out we're not correcting for temperature that affects the speed of sound that affects measurements. So anyways, so that was the prototype we did. It was just basically a tube. Now we're evolving this concept by using these things that we call voxels. And then we can compose them with each other, and then we can fabricate arbitrary linear filters that shape the frequency spectrum. So it's not a robot, but it's pretty cool in my opinion. Okay. So these are some examples of how security affects real world systems that have safety implications or security implications. So in the research that we do here in the security and privacy group at UW-Madison, we take a perspective. How can it be broken? So we look at these systems, then we say, how can we break these systems? And then we try to make them more secure, more safe, and more private. Cool. So these are some of these are the main research themes that cover our research. Trustworthy machine learning, but actually now these slides are too old, right? So what do we say now? Trustworthy what? AI, right? So these are outdated slides. They're like 1 year old. This slide, I mean, I updated other slides. We work on data and sensor privacy, user authentication, privacy preserving human factors in security and privacy, and decentralized system security. I'll give some examples of the research happening here. I'll be a bit brief, so that we're all back on the schedule. Okay. So one example of making machine learning systems more robust to attacks before is to leverage domain constraints. For example, a stop sign should look like a red octagon, right? So a model should be able to use this information to do its inference. So in one of our research projects, we used a LiDAR to sense the stop sign, and then you say, well, use the LiDAR, use the image as well, and then you might be able to get a more robust classifier, right? Because you can actually get the silhouette or the shape of this object from the LiDAR. It's like a depth reading. Other example of research in terms of data and sensor privacy is we look about how do systems collect data and how can we prevent them from collecting data. So one research we did a couple of years ago, we analyzed the privacy properties of mute button and video conferencing apps. And we discovered, for example, WebEx, when you mute your microphone, it still accesses the audio data. So muting doesn't really mute. And that got us an interview on the BBC, and they asked us, do you want to do a live interview on BBC World? I told them no. And then a few hundred million listeners like, thank you, I just recorded it. We also work on next generation authentication systems. For example, Rahul works on how can we make passwords more robust to typos. So you type in a password, you might have a typo, but it should still provide security property. We don't want to log you out. We also have other authentication methods based on biometrics, like using accelerometers and other kind of sensors to have more robust authentication systems. We work on privacy preserving machine learning. This is one of our newer faculty, Rishabh Goyal. He works on making machine learning more privacy preserving. Now, a big problem in machine learning is, let's say you have multiple hospitals and they all have their own data, but they want to train a big model that leverages all of this data. But nobody wants to share their data with someone else, right? So we need to do this machine learning in a distributed fashion. We need to train a model in a distributed fashion. So we need to do that while respecting the privacy of the data. So there are lots of paradigms around this. And one of Rishabh's research is how to perform that while computing on encrypted data. So nobody can see the actual data. You compute on encrypted data, and then you get some useful insights out of it. Pretty cool, right? You can nod, it's okay. One more research in terms of human factors, security, and privacy. Rahul works on preventing technology abuse by looking at these dual-use apps that can be innocuous when you look at them, but they can actually be used in abuse situations, especially inter-partner violence. And then he analyzes them and then understands how do they affect people in practice. And Rahul also leads the tech clinic on campus, which takes abuse victims and tries to help technology abuse victims and tries to debug their problems and help them. Ethan works on decentralized system security. I'm not going to tell you about this why, because you're going to hear from him in 2 minutes. So I'll just skip this. Cool. And this is the faculty. These are the faculty who work on security and privacy research at UW-Madison. So Paul Bartford is at the intersection of security and networking systems. Bart Miller is on the intersection of fuzzing and software assurance, bug finding. He teaches our software security course. Tom and Mike Swift work on trust management, model checking, and intersection of security. And Rishabh, as I said, works on advanced crypto, and he's applying advanced crypto methods to privacy-preserving machine learning. And this is how I looked like when I joined UW-Madison. Younger, no eyeglasses, black hair, lots of, this is what like 7 years of tenure track does to you. So these are the security courses we teach here. We're planning to expand these offerings, but this is the current slate of courses. We have an intro to crypto. We have software security, which Bart teaches. We have an introduction, a more general introduction to computer security, where we cover software, networking, and other things. We have a data security and privacy and data science. So this is more about the theoretical aspects of privacy, like advanced crypto, differential privacy. And then we have advanced topics and security, computer security, which is more on the systems side. And these are graduate level courses. And come to Madison. Thank you.
Hi, everyone. My name's Ethan Cicchetti. I'm a new assistant professor here. I work sort of at the intersection of programming languages and security, and unfortunately, we seem to keep downgrading, right? You got a robot, then you got the little voxels. I have nothing. I'm sorry. It's just me. But I want to talk about the PL group, and hopefully I'll get us the rest of the way back on schedule. Thank you, Qasim, for getting us most of the way back on schedule. Right. So the fundamental question that we tend to ask in the programming languages group here is should programming correctly, at least, be this hard? Right. It's really hard. Qasim was just explaining a bunch of ways that it's really hard to write programs that do the things that we want them to do. And he was talking about it from a security standpoint. But there's also problems in other ways, right? Software is everywhere. And we have tens of millions of software developers in the world. And software is doing all sorts of crazy things for us now that it didn't used to do, right? We have very complicated networks. We have all sorts of data science applications and pipelines that are trying to clean and filter and extract data and then do interesting things with them, right? We're building all sorts of machine learning models with our software. We're using software to make decisions that maybe we shouldn't be making with buggy software, and we can have an unrelated discussion as to whether or not it's a good idea to make them with any software at all, but we certainly shouldn't be making them with buggy software. And we need tools that software developers can actually use to program these systems. And the goal of the research that we do in the PL group here in a lot of different ways is broadly to try to create tools to help software developers meet the needs that and actually develop software that meets the intent of the developer. But this is really, really hard to do right now. Debugging is basically a gigantic industry unto itself. If any of you have spent time working at large-scale software development firms, you will know that if you spec out how much time it takes you to write a piece of production software, you figure out how much time you think it's going to take to write it, and then you double it because that's how long it's going to take you to actually debug the thing. So there's an estimate, right, that the cost of debugging has risen. This is old. 8 years ago, the cost of debugging had risen to something like $312 billion a year. It's probably way higher than this now. I didn't go try to find a new number on it, but it's probably just absolutely enormous. So the question is, what should we do about this? And that's where we come in. This is the PL group here. I want to note that Laura Stantoni is not on this slides because unfortunately for us, he will be leaving the institution at the end of over the summer for personal reasons. He's moving elsewhere. So I'm just going to talk about the five of us who are up on this slide. And we all focus in some way or another on how to build code that works. And there are really three parts to building code that works. We have a specification. What is the code supposed to do? We have the code itself. This is what's actually defining what happens. And then we need some sort of a proof that tells us that the code meets the specification. The code actually does what it's supposed to do. And what the programming languages group here does is we essentially work on a toolbox that we put in the middle of this to try to connect these three things up with each other. And we're trying to build and improve this toolbox. And all five of us work on this toolbox, but in various different ways. So Tom Reps and myself work, broadly speaking, on the idea of sort of language-based security tools. So we take the code in the spec and we sort of add this extra little tag onto the spec. Usually it's a security-related specification of some sort. We're going to take those two and feed them into our toolbox, and we're going to try to get a proof out the other side, or a bug or an error or something that tells us that it isn't actually secure. That would be fine too. So I'll spend a little more time on my research in particular, right? I focus on something called information flow control. This is actually the slide that Qasim had up that he didn't explain. I'm actually going to go through it now, right? So let's say we have a database that has a bunch of medical records. This was inspired by the fact that we have a very large medical record software company just down the road from us here. And maybe there are some patient records in that database, but there's also some other stuff that's a little bit less sensitive. And we feed all of the data in this database into some system, and there's a bunch of users on the other side, right? Maybe we have some doctors, maybe we have some administrative users, some administrators at the hospital or something like that. And the doctors should probably be allowed to see sensitive patient data. They kind of need it to do their job. The administrators, maybe less so. Maybe we shouldn't be giving them sensitive patient data. But there's a problem. If we want to know that this system meets this specification, we can't see what's going on in there. We don't know what's happening. So how do we actually check to make sure that that sensitive patient data isn't going to leak to the system administrators? So the idea behind information flow control is that we want to track how data flows through the program. The research that I do, I tend to do this with types. So you might think of types in a programming language as something like int or Boolean. Those are great types. I use a lot more complicated things. I use types that are able to make statements about who is or isn't supposed to see this data and track how it can actually flow through a system. And so it lets us open up that black box and turn it more into a white box where we can actually see what's going on inside, and we can track to see, oh, this red line sort of only goes up to the top. There's no red line going down to the bottom, so this is probably fine. The research here has a lot of interesting questions. This is really hard to do for complicated, large, distributed, and concurrent systems. It's currently really hard to use in practice. I have multiple active research projects trying to address the first one. I have a few ideas for research projects that I really want to spin up that I need really motivated and excited students to work on to try to solve the second one. So I sort of think of, one of the tools from the toolbox, I decided to pick a screwdriver for no apparent reason, is to use these security types to solve this problem. This has some benefits, right? It's really, really fast and easy to use, as it turns out, but it's also extremely restrictive. And so my goal is sort of to make this tooling a lot less restrictive, make it easier to use, make it apply to more systems. If we look at something like what Tom Reps is doing, on the other hand, he uses program analysis. I don't have time to go into this in the same level of detail, right? But his program analysis has a different trade-off. It's more of a Swiss Army knife. It's extremely expressive. He can talk about he'll talk about programs written in all sorts of different languages with all sorts of different complicated specifications that my research just doesn't have any way to express. But the downside of this is that the mechanisms to generate a proof or find a bug are often much slower. They don't scale anywhere near as well. And so a lot of that research, the goal is to make this scale better in more places, make it usable across more pieces of software. Moving back a little bit into sort of a different viewpoint, Tej Chajed, you will hear from later this morning. He'll be talking about the systems group here. He also sort of works on the edge between two groups. He does systems verification. So he takes all three of these. Oop, that box was supposed to disappear. Oh, well. And feeds them in to one tool, and that tool spits out a yes or no answer. And he tries to do this for really large scale real systems. So for example, trying to verify that a large distributed key value store actually does what it's supposed to do while still being highly performant without slowing it down at all, right? How do we make sure that it's actually behaving properly? How can we verify this? And so the specification here is essentially any notion of works right that you want it to be. And the code is any sort of large scale system that you want. The downside here is these proofs are really large. They're really challenging to write. And you notice this arrow here is a blue arrow feeding into the tool. That means the developer has to create it for you. It's not going to spit it out automatically. But the goal here of a lot of the research that he's doing is to make this easier to use. Make it easier, make it faster, make it more accessible to more people. We can turn a bunch of these arrows around and talk about program synthesis. So we have people working on program synthesis up here, where you feed in a specification and it feeds out code and a proof. So a specification here might be something like, I would like a function that sorts lists, please. And it just automatically generates the code for you. The proof is sort of trivial. It's almost by construction. If your synthesis mechanism is working correctly, the code's going to do what it's supposed to do. The downside is that this only works right now for very small programs and relatively simple specifications. And so the goal here is to expand that, make it work in more places, make it work for more types of code, make it work for larger systems. In fact, Aus's work in particular actually does a lot of work with quantum compiler synthesis. So this is a place where it's really trying to work with more types of code. So in this case, the specification is actually a quantum computing device. What are the parameters of that device? And this is now a sort of bidirectional arrow, because you put a quantum program in, and the goal is to get a much faster quantum program out the other side that is specifically tailored to run on this device. And the proof is that the program that got spit out does exactly the same thing as the program that went in. And that, again, green arrow coming out is automatic from the system. And this is done using a variety of tools involving SAT solving and rewrite rules and synthesis. Harkening back to something that Qasim was just talking about a minute ago, right? We have machine learning robustness questions, but we're doing them from a programming languages angle. So in this case, the specification here is a question of robustness or a question of fairness. We have to define what that means. That's a challenging problem. But it could be something like small changes to the data don't actually change how the model operates in any observable way. And the code here is going to be the data and the model that goes in. And we want to spit out a proof that it's robust in an as automated a fashion as we possibly can. And the goals here, right, are we want to strengthen these results. We want to get proofs for more models. We want to be able to talk about more things. We want to more precisely identify when they do and don't actually work. And all of us are using sort of a similar toolbox here, right? And we've all got our eyes on these three, the specification, the code, and the proof, these three sides, and we want to make sure we understand how they connect so that we can build programs and build systems that really, that we know we have a proof that the code meets the specification, and we're doing it in a variety of different ways. So that's all I have. Hopefully I'll talk to some of you this afternoon.
All right, good morning. Welcome to Madison. My name is Xiangyao Yu. I'm an assistant professor in the database group, and I have been here for, well, 4 years. This is my 5th year. So I'm going to tell you a little bit about the database group here. All right. So the database group here has a long history of success. You probably heard of the relational model, like this foundational model for modern databases that says we should organize data as tables, and the tables can have like different columns, and the tables can join with each other. So that was proposed in 1970, and the Andrew Codd, who developed this model, won the Turing Award. Well, he's not from here, but very soon after this was developed, the database group was created in UW-Madison. And this was very early because this was one of the first database group in the country. And at that time, because it was very early on, well, database was not even considered as an independent research area at that time. But well, Professor David DeWitt was really, well, forward-looking, and he created the group. And since then, there has been a lot of success in the group. So it has been the leading database group in the country for many, many decades. And we have had a lot of successful professors throughout the years, while some of them have retired or have moved to industry. And while there have been leaders, some of these people are leaders in big companies like Microsoft or Google. Like they are very senior and high level. They're leading important research and development. And not only we have successful research, we also have a long history of student success, right? So students in the group graduated, they have joined, many of them joined academia and become professors in places like Berkeley, CMU, or EPFL, etc. And also a lot of students went to big companies, and some of them, well, if they graduated 20, 30 years ago, now they become the leader of these companies. So every time, actually, if you go to a database conference, there will always be a big group of Wisconsin people. So it's like becoming a tradition. Like when we go to a conference like VLDB or Sigma, we will take a Wisconsin picture with all the people who have Wisconsin affiliates, and you will see there's a lot of alumni industry, and so it's very powerful, and it's also very helpful for your career in some sense. Okay, so right now we have 3 professors in the group, Professor Anhai Duan, Paris Koutris, and me, Xiangyao Yu. And we also have a few affiliates, well, some of them are professors before and they retired, or there are people, there is a Microsoft office in town and also a Google office in town. And in both offices, they have a lot of research in databases, right? In a sense, I think the Microsoft office was created here partly because of the database research is very strong here. It's called Jim Gray Lab, and Jim Gray is another Turing Award winner in databases. So, and we also have a lot of students. So it's pretty active and big group. So in the group, we study everything related to data management. So you can think of this as nowadays, the data size has been growing. And a lot of research or development in computer science is all about, here's the data, well, what can you learn from it? Right? Machine learning is about that. You use different, maybe deep neural network to extract insights from your data. And database is kind of taking a slightly different approach, but it's all about having all of these data. How can I learn from the data? Like what insights can I extract from it? And well, you develop theory, you develop systems, algorithms to serve that goal, right? And we do things like data cleaning if you have a lot of data, but it's probably dirty. Like different users may submit their data in different formats. How can you clean it up so the system can actually make sense of it? And we do transaction processing, you can think of this as buying some stuff online, making payments, how to make sure that's secure and reliable and efficient, performant. We do data analytics. Well, basically, we also do machine learning and AI. Well, nowadays, everybody does it. So we use machine learning to improve databases in all aspects, right? So I will go through the research of individual professors quickly. So Professor Anhai Duan works on data integration and data science. So for example, here I'm showing one example of what the problem might be. So let's say you have these tables of users of a, I don't know, maybe some system. And in one table, users put their information in a specific format. They say, okay, here's the name, you have the phone number, you have the city, the state. But maybe in another table, this is like 2 different applications or 2 different website forms. So in the other table, people also add their information, but the format is very different. Like the name now has a middle name initial, and the phone number is also slightly different, right? So now the question is, how can you tell that these records refer to the same person or not? It's very helpful, right? If you know they refer to the same person, then you can connect these two tables together. And you can do some further analysis. But if you just directly look at it, well, as human, we know, okay, maybe the first row in both tables refer to the same person. It's obvious. But for a computer, how can you figure it out? And there, you can do a lot of rule-based matching, or you can do some machine learning-based matching. But that's the question we're trying to answer. In this simple example, you may come up with a solution immediately, but in practice, it can be arbitrarily complicated, right? So this is a very important question in industry, because if you can figure this out, you can imagine a lot of things. Now you can do a lot of analysis to make a profit. So Anhai study this entity matching problem and also a lot of other stuff. In particular, Anhai also builds real systems. So it's not just about writing papers and building like tools in lab to test the algorithm, but it's also about building real application that can solve this problem in practice. So I think Anhai has got involved in several companies already. And this is the most recent company he created and got acquired by Informatica a few years ago. And I think he has been the vice president of Informatica since then, maybe until recently because of the acquisition. Okay, so Professor Paris Koutris works on the theoretical side. So he studies, for example, one project he's working on is a topology-aware parallel processing. So you can think of it, well, nowadays, many systems are parallel. Like even within a single machine is always parallel because you have multi-cores. And more data processing is happening in distributed system, right? Because, well, your data is too big, it doesn't fit into a single machine. And also, a single machine does not have enough computational power to process the data. So getting increasingly distributed. But now the question is, distributed system always have different topology. Like if you have within one data center, you may just say, okay, let me just have 8 machines and connect them like all-to-all connection. Well, that's fine, that's easy. But what if you have multiple cloud? You have some servers in your private local cloud, but some servers in Amazon or AWS, sorry, Azure or Google GCP. And now you have a more complex topology. And you may also imagine things like, oh, you have a CPU, but you have a GPU. But now you have even more complicated topology. So because there are so many different topologies, how can we come up with a framework so we can design algorithms for different topologies, right? And come up with some principle to optimize for different topologies. So that is what Paris has been working on. Some other projects, for example, as I said earlier, your data is usually not so clean. So what we have been doing, well, we can clean up the data, which is very difficult. But once you clean up the data, you can do analytics. Well, can you not clean up the data? Can you directly run your analytics on the dirty data? Well, you may get some incorrect outcome, but can you get some correct outcome? Like what can you bound this? Like if I run my query on dirty data, then what information am I going to learn? What am I able to learn, right? So that's another way of dealing with the dirty data problem. And finally, I work on the system aspect, like cloud databases and new hardware. So you probably know cloud database is pretty popular these days. But if you look at it like 5 years ago or 7 years ago, cloud database is like a tiny fraction of the database market. It's probably less than 10% or maybe less than 5% of the database market. And back then, people deploy their own clusters. They run their own machines and install the software, and that's how people run databases. But now, more than 50%, maybe 60% now, more than 50% of the market is in the cloud. And more than 80% of the database are deployed in the cloud. Okay, so this growth is tremendous and happened within only a few years. And using a cloud database is way easier for users. You don't need to get a servers and install software. You just go to the cloud, get a web page, and say, I want a machine with, I want a for machine with Postgres. You click, now you can run SQL. Like it's super easy. And you pay only for what you use. Like you use it for 1 hour and you say, I don't want to run any query anymore. Well, after 1 hour, you only pay for the very cheap storage. You don't pay computation. Like this is very attractive for users, but this also creates a lot of new challenges and opportunities in terms of system optimization, right? For example, they keep the storage separate from computation. Well, that's a fundamentally different architecture. Okay, optimize for that. Another thing is another exciting thing happening in my lab is the GPU database. If you look at the trend of GPU computational power growth, it's amazing. The CPU is not getting faster anymore, but GPU is getting faster. Like the performance doubles maybe every 2 years. So within a few years, GPU will become so much faster than CPU, maybe become no-brainer that you have to use a GPU database if you care about performance at all, right? So we think it's super interesting, super exciting to work on this. Like I think in our lab we have one of the fastest database prototype in the world because we use GPU to accelerate. All right. So in summary, we work on everything about data, and there is the DB open house this afternoon from 1:30 to 3 in the CS building room 3310. And after that, we will keep having these meetings, but after that will happen in students' offices. So hopefully I will see many of you this afternoon. Okay, thank you.
All right. Let me navigate. All right. So my name is Yasel Kim. I'm here to introduce our group, graphics / visual computing group. We are investigating model, algorithm, and tools or systems for the applications that end user sees or interact at all. So I'm going to unpack this, what I mean by it in a few slides, because it's really covers a lot of various range of research. And then our group consists of 4 people here. Iftikio suffices, and then Michael Gleicher, Yuhang Zhao, and me, Yasel Kim. I'm going to go over one by one how each faculty work on their research. So Iftikio's research covers diverse aspects of computer graphics and animations and simulations. And then spanning of these topic in this slide, which is like physical-based modeling, as well as digital humans, like simulating the humans in a digital world, and simulated virtual materials and fluid animations and fracture and mayhem. You'll see some of the mayhem over there, and then fast math in generals. So this is a quick examples of simulated virtual humans. So he develops models and algorithms of how human work out, how humans swing, so that eventually that he can simulate these movements in the virtual world. So by how he does it, like he models how human moves and mathematically formalize that to apply to the applications that involves these movement to be simulated. Another examples here are the animated characters where you can kind of simulate all in the body parts, that how it moves and so on, as well as how the hairs get laid out, how thinly hair can move and so on. Those are the part of the animated characters research. The next one, which is a very impactful one, which is sometimes the cutting for virtual surgery, where models how human skins laid out or how it works, so that it can give some safe space for a trainee for surgeries and so on. And then this one is more of like a nose skin removal surgery and so on. And so you can use these applications for doing that. So sometimes he break things up, like creating some chaotic scenes and so on. And the next cool things, but involved about the smoke effects. Again, the modeling the real world, the phenomenons of smoking, and then mathematically formulated and then applied to this real graphics so that this looks really realistic, as well as really the pursuit for the realism as well. Next one, similar one, which is fluid modeling. I guess like application wise looks similar, but probably that a lot of different elements in the real world needs really different perspectives to models. So this one is specifically for the fluid in the real world. How can we model it? How can we simulate it? As well as like, can we make it really high resolution? Some of the emerging interest of his is about like how can we optimize the shape for the 3D printings because this machine is like emerging technology, and also he's interested in some of the muscles movement in motion control that this similar approach, like how can we model the real humans movement so that we can apply this models to the applications like creating the movement of the humans and then like throwing the balls and so on. Another research of his, the working with the motion picture studio, where this is with Disney research, where take a human as an input, the real human, and then you can kind of re-aging those face. And actually you can make it younger as well, the older as well, by using some the deep learning models to simulate these aging simulations. This one was another application that he worked on, which is like motion pictures. How can the neutral face look like, and how can you like manipulate the facial elements to convey some of the face expressions. Next up is Michael Gleichers. Professor Michael Gleichers has like very diverse interest spanning from human graphics interactions and human robot interaction and human data interactions. So basically he's interested in anything between human and any computer supported artifacts or medium that involves visuals. So his interest actually started from graphics. He started his career as a graphics researcher, and he teaches graphics classes as well. So if you're taking his class, then you'll get to, I don't know, that's the one of the assignment, which I felt like really cool. So you're going to design the train track where like, if you make it 3D, it becomes roller coasters. That's one of the assignments that you'll get to learn. You'll get to understand how to design curve graphically, and so on. This is a little more of the actual project from his class. The students get to build the graphics and animated graphics to reconstruct virtual worlds and any other animated or static graphics. So the next interest that he has is robotics, which is described in another talk. I'm not sure robotics is already done or not, but he will be covering those in that sections. And then there's the open house informations. So lastly, he's interested in visualization research. So not only visualization research, but visualization practice, visualization education. So visualization, what I mean by here is that you can simply think it as charts and graphs, but anything that encodes any types of data, we call it data visualizations. In shorthand, it's visualizations. So the visualization research is about like developing the science, which is like figuring out the principles of like how we should visualize things. Visualization practice help domain collaborations where like how can we support the practitioners where actually visualize design on daily basis. Visualization education is partially about teaching how we should teach how to design and evaluate good data visualizations. So let me briefly talk about this visualization research part, where you can think as like a 4 different subfields. So the perceptual study is about when you really think about what to design or how to design visualizations, what we need to understand is how human vision works, right? How vision can cut patterns, how vision can detect any distinct elements, visual elements, and so on. So perceptual study concerns about like very elementary levels, very rudimentary levels of like how human vision works with the simple visual elements levels. For example, like can they detect the different colors? What is the difference between like 2 color has to be noticed as a different colors and so on. It's very perceptual, basic science level. On the right corner, technique designs, when you can think of like all sort of different data type, there's like vectorized data or list of data, but also there's hierarchical data as well as there's high dimensional data. There's all sort of like different formats available in the world. And then technique design research mainly concerned about what would be the best way to incorporate or like visualize those types of specific data types, it has to be really different intuitively, right? So it's a hierarchical, then you have to convey the notion of hierarchy out of visuals. If it's a high dimensionals, then human vision cannot detect more than 3Ds. How are you going to do that? There are specific techniques related question involved in this research. On the bottom left, there's a system research where we call it like visual analytic systems. So you can think it as a end-to-end applications that concern about visualizing different types of data sets, but as well as understanding how the end user might use this visual analytic systems, so that they can achieve their own analytical goals. So the system research involves how to identify the end user's goals, as well as how can we lay out things, different functions in the space of this tool so that the people can interact smoothly without any issues and so on. And then lastly, the exploration of principles. I'll say this one, when you do a lot of like perceptual study or technique designs or all tool designs or building systems, you get to understand a lot of different insights out of like, how should we even design a visualizations? So this exploration principles often aggregates all those insights while doing researches, and then try to understand the landscape of it. So what types of principles should we derive out of those insights? So in his lab, he's doing some of each of this quadrant, where some of the system research, some of the his student and he built some of the systems to support the domain science and the technique research, as well as some of the perceptual study that he ran so far. The latest work of his is abstract viewers, where like how can we support the people who search abstracts of all papers. So this viewers supports many different types of visualizations to show like what you should read and which abstract is located where, and then try to give some big landscape of like all the papers that you need to read and so on. So Graphics Lab Open House information is here. All right, so we have 4 people, so 2 more to go. So Yuhang Zhao, Professor Zhao's research focuses on AR, VR, and accessibility, developing AR, VR technology to make both the real and virtual world accessible to people with disability. So she's mainly concerned about people with motor disability, as well as the visual disability. So people who cannot see or has a low vision, that's her target of study. So when you look at the left corner, supports how to read text better when you have a limited vision. And then on the bottom, there's how to support the cooking experience through the AR and VR technology to better supports their real world experience. So her talk or her research will be covered in the HCI talk in a few hours or a few minutes. All right, so next up is my research. I'm serving the similar target people as what Professor Zhao would do. So I'm interested in people who with visual impairments who cannot leverage their vision. And I'm not sure how many of you seen visualizations or data visualization already today, where this is very prevalent, where we never finish our day without seeing any charts or graphs. At least as an academic, I've encountered it almost like hourly basis. My research and my lab's research started asking like, yeah, I mean, visualization is really powerful because it summarizes a lot of patterns. It surfaces the some insights of the raw data. It's a lot better than just eyeballing the raw data. But what if you can't see? What if you have a limited visions, or you're blind, or you're low vision, so that you can't see these visualizations? So our research started by asking this question: how can we convey the same informations when people cannot see? So I'm studying people with visual impairments mostly, and then try to understand what would be the best way to translate the same visual signals to other modalities, such as it can be text, it can be auditory signals, it can be like sounds and verbal, non-verbal sounds, but as well as a tactile. How can we migrate this information exactly into the tactile space so that there's no information loss? And then, yeah, so let me show you a few more examples. So we're mainly concerns, most of our lab's research concerns about like text modality. So what if we can convey exact information as visuals convey through text, right? Because thanks to like large language models, it seems like plausible. So there's such a thing like alternative text. I'm not sure you've heard of it. So when you visualize some of the any image that you uploaded on a browser, you technically have to add the alternative text where the screen reader users can access to. So this mainly blind and low vision users use screen readers to explore the web browser. And then there's alternative text where like they can't see the image, but you can access to this text where you can get the sense of what the object or visual elements are laid out. So we're interested in like how to formulate a good alternative text where like by identifying what makes an alternative text a good one. If you're blind and low vision individuals, what types of components do you want to look for? What types of information you're looking for to get out of the same insights as the visual viewers. So we study the principles of like what makes a good text summaries. And then next up, once you understand like what makes a good alternative text or what makes a good text summary, you want to automate that using a lot of different computational techniques so that you can kind of automate and scale up with the same approach. So we're mainly looking at whether the different chart type of it, the left one is kind of line charts, the middle one is kind of heat map, but the complexity of visualization, the complexity of data type makes it difference in the components or design principles they have to follow. Lastly, we're working on some other modalities. So the table is very well designed human visual artifacts to show data as well, where we don't really think in that way, but it really leverage a lot of human visual metaphors. So when you look at it, there's like a highlighted blue that you immediately think that you're grouping in the column without even thinking. And then there's empty cells. Of course, empty cell is empty value. If there's a merge cells, then it sort of like magically provides some notion of like grouping elements. So this table, which seems basic, but it really effectively leverage human visual metaphors to smoothing out your interactions of data. But if you imagine this with the screen reader experience, if you have to like navigate one cell by one with the auditory experience, how can we support that experience better so that people can understand or people can navigate this table as the visual viewers? All right, so that's all of my talk today, and then I'll look forward to talk to more of you. Thank you.
Good morning, everyone. So today I will talking about some of the work that we have been doing in the networking group. So when we're talking about networking, it's all about connectivity. Basically, the fundamental problem that we always trying to solve is like how can we really connect computation resources in an efficient way and expose them to the up layer system stacks. So the problem that we always trying to do is like we want to build fast, efficient, secure, and reliable network systems and protocols at different scale. So when we're talking about fast, we basically refers to the fact that we really want to maximize the physical limits. So for the wireless case, we want to ensure how can we deliver the maximum of information bits for a radio frequency, and in the wired network, we want to see how can we really maximize the utilization for the underlying communication medium. It can be optics or it can be copper. So when we're talking about efficiency, we mean many things. It can be energy efficiency in terms of like for a particular joule, how many bits you can transfer, and you can also talking about cost efficiency. But for networking, a unique point is multi-tenancy. It's unlike many of the application domain that you are working on. From networking perspective, we always consider multi-tenants, like think about the underground networking course that you have to take. There's one important problem we always trying to figure out is how can we do congestion control to allocating bandwidth efficiently for different networking traffic. And then next bit is regarding secure there are two perspectives. One is like we want to minimize the attack vector, and simultaneously we want to develop fast mechanisms to do security prevention, or like we want to do detection. Basically, if you think about security, the data is transferred over communication medium with literally no supervisor. So we literally need to find a way to see how can we ensure the communication systems such that like, there's no information leak. And the last bit is regarding reliability. We probably one of the major claim always for networking research is like when something goes down, it is always the problem from networking researcher. However, when we're talking about reliability, we want to really minimize the zero downtime, but we also want to developing tools so that we can easily identify when something happens, whether the error is coming from one particular networking links or from one particular networking fabrics. So in networking research, we consider all kinds of skills. We consider system on chips. For example, we consider how different IP modules on a single chip, like how do they communicate easily. We consider wireless case like cell towers. We consider all the edge devices that you guys have been used frequently. We consider at the board level, like suppose that you are working on computer architecture, you will know okay, there will be many emerging boards that has many more accelerators being developed. We also consider how can we minimize the communication cost. And finally, we're looking at rack scale, cluster scale, or even data center scale. Probably that's the most challenging part. So this is fundamentally the goal for networking research. In order to build networking systems, there are many hard problems. So from our perspective, make everything connected is not that hard, but make everything connected in an efficient way is mostly the challenge. Therefore, the way we explore problems usually from three perspectives. So the first perspective is from new applications. So for networking research, you have the capability to enable new applications because of the new communication capability you provided. For example, like when people have doing on is like they have built battery-free communication medium with this kind of new device. You are able to do literally no battery-less sensing mechanisms. However, we also from another length, which is like we want to build networks for emerging applications. There are many emerging applications. For example, we see functions, we see blockchains, and we also see probably there are too many AI stuff. But one thing you probably want to really think hard is, suppose you have lots of GPU devices, how do they really communicate together? It is not the case like you build your bespoke workstation have 8 GPUs built in, but how about if you have 100, how do these workstations being connected? These are kind of the problem that we want to address from our perspective. So the second length in terms of driving factor is new hardware. So there are two types of new hardware. One is networking hardware. If you're looking at all the networking vendors, there are new networking hardware comes in. They're providing more programmability, but simultaneously they will emphasize like what is the bandwidth and latency being improved in the next generation. So that's kind of the new hardware from networking perspective. Another perspective is like we have new endpoint device. Because we want to connect things together with new endpoint device, we want to see how can we build our networks. A new endpoint device, you can see they are storage device, they are computing device, right? They are you can see there are lots of flash comes in, then how can we deliver networking systems efficiently to get the storage being built into your system? And the last piece is new experience. As I mentioned before, if you're starting from scratch to build connected systems, it's always not that hard, but how can we really manage it in an efficient way is become the challenging. The fundamental challenge here is we want to get enough observability of the networking. We want to see how traffic has coming through different parts of the network. Like we want to see how many packets has gone through one particular link, one particular port, and one particular switch. In order to do that, we want to get in the data and do optimization. Therefore, the new experiments are usually coming from measurement perspective. But in order to do such kind of measurement, how do you do this? You want to build utilities. Therefore, another length here is collaboration. You probably will see many of the networking researchers collaborating with PL systems and also machine learning systems. They want to build some kind of newly capability profiling systems such that we can get this new observability. So these are kind of three driving factors for networking research. Next, I will talk about some of the work that we have been working on. So there are three faculties in the networking group at our department. Professor Paul Bufford is working on internet management. It is mostly coming from the third driving factor, new experience. And Professor Sun Banerjee is mostly working on wireless and mobile systems, edge computing. His perspective is mostly coming from the application side. And I'm mostly working on cluster interconnect program networks, which focusing on emerging network hardware. So next, I will talk some of the work that we have been doing. Hopefully, if you got a chance, you can talk to them in details regarding some particular projects. So Professor Paul Bufford mostly working on networking management. Therefore, it's trying to improve networking performance resilience by understanding more about the underlying internet infrastructures. In order to do this, therefore, we need to getting data from the internet and then apply a bunch of analytics systems, and then we also need to build new utilities. Therefore, the research style is more empirical and experimental. If you are interested, you can check the Will's lab. So one important question that he's trying to ask recently is trying to asking what is the climate change to the underlying internet infrastructure. Probably you have seen lots of news like the bird optical fibers in coastal areas at risk because of the sea level increase, and also the cellular infrastructure is under the risk of wildfires. Therefore, with such kind of climate events happening, how does it really impact your communication performance? Therefore, this is kind of one important question he's working on. Another one is regarding a new perspective, which is internet vibration sensing. This is kind of a really new thing happening. So the problem is regarding ground motion and structural monitoring. So if you have buildings, you want to do this. Therefore, sometimes from architect perspectives, you kind of need to develop some monitoring infrastructures to keep monitoring these two stuff. But the question they ask is like, instead of get this new development equipment embedded into your buildings, can we use an existing network infrastructure? Basically, the question here is like, by looking at the existing network infrastructure that already being developed into the buildings and then keep monitoring the vibrations, whether we can use such kind of signals to do ground motion and structural monitoring. So one example like in YouTube is quite famous is like if you speak to a hardware drives, you can see the performance actually change. So this is kind of go to the similar sense. Next, I'd like to talk about Professor Sun Banerjee's research. So here is kind of the outcome from his group in the past years. So his group has operated their own 5G network on campus. I think this 5G network basically including everything you want to see from RU side to DU to CU until to the mobile core. However, this will not be that high frequency. And they have their own TV white space networking systems. They have lots of wireless testband being developed, and there is the internet on wheels between a project that putting wireless devices into the bus, which is driving between Madison and Chicago. For example, one area that he's working on is trying to analyzing your driving behavior, because like if you're driving your car, you're always asking these questions, what is my driving behavior? So if you think about this, how do you really do this? So one way we need to do is like, okay, we need the monitoring system. And this monitoring system should be embedded into your car, which basically means it should be battery efficient, right? There's no external power. Therefore, after you get that monitoring stuff, then you want to deliver the signal into analyzer, and the analyzer is on the edge side. And then after you deliver to the edge side, you want to do analytics. So therefore, if you're looking at this project, basically it's trying to combine everything in an end-to-end pipeline such that you can have those question to be answered. So this is kind of one project. Another similar examples is regarding healthcare. So right now, many of the healthcare equipment currently have this wireless sensing informations. They can keep gathering the data. So if we throw out the security concern, just focusing on data, which basically means after we get all these monitoring informations, we want to deliver to the edge side for analytics. Therefore, they have developed this Parajob project to enable those. So this is another case study. some new directions that he is currently exploring is regarding satellite networking and space IoT. I guess probably some of you have already frequently used Starlinks for your communication. So if you are interested in this kind of size, feel free to talk to him regarding some of the ongoing efforts from his group. Finally, I will talk a little bit regarding what I'm working on. So I'm mostly currently focusing on rack scale composable infrastructures. So basically, this is fundamentally driven by some specialized cluster interconnect. With this special cluster interconnect, we are able to do many things. Firstly, we can unify the intra-server and the inter-server communication. As a result, we bring many devices that are quite close. So later you will see an example. And then we also see, like, for such kind of cluster interconnects from the networking component perspective, what is the capabilities? And finally, we want to see not only computing devices, but also endpoint devices like DDR5, HBM, and also new storage device. We want to see how can we do in this composable infrastructures, such as we can bring all these communication devices together. Probably the question you will ask is like, what is the difference between what happens right now compared with what happened in the existing racks? So if you got a chance looking at today's rack systems at any size, what you will see is that you will have a rack of servers, and inside each server, you will have compute networking card and also switches and also memory resource and storage. So that's what's happening today. But none of them really happening because like in this composable infrastructure, basically, the fundamental thing enabler is pooling. What I mean pooling is like you have resource pools, like which is physical resource pools that have accelerators, just accelerators. You have resource pools, just memory modules, and you have resource pools, which is just the storage. Because of resource pooling, you will have on-demand scaling benefits. You can have more better consolidation. As a result, it kind of providing you a vision of big computer. So the fundamental problem we want to see is under such systems, how can we really build something? So here's an example, which is one testbed that we do. Basically, it is a PCIe fabric. It's a routable PCIe fabric. You are familiar with PCIe because on your workstation, you have GPU, right? You connect a GPU card, it works. But think about if I want to connect the 16 GPU cards, how do I do? Basically, in our testbed, what we do is like we have this endpoint adapter connecting to the server, and then there is an external PCIe switch and the standalone chassis. These are all PCIe-based device connected through Gen 3 and Gen 4, or even Gen 5. And then go back to the question, if I want to get 16 GPU connected, what we do is like we connecting the endpoint adapter through the PCIe switch through a copper cable, and then using copper cable connecting to the standalone chassis. And in that chassis, let's put in more device. That's where what we see. And then from the server perspective, if you log into a system looking at your PCIe bus, then you will immediately see 16 GPUs. That's what we enabled in this kind of infrastructure. Therefore, our group built stuff, and hopefully we can build efficient. Therefore, fundamentally, we want to rethinking the control plane and data plane when we're building applications together over such composable infrastructures. There are three research thrusts that we do right now. One is like we're looking at emerging cluster interconnects, which is the line that I showed before. And the second thing, we're looking at storage. Last one, we're looking at program networks. So if you are interested, feel free to talk to us. So our schedule is like one meetings in the afternoon tomorrow. So if you have additional questions, feel free to send us email. Thanks.
Hi, everyone. My name is Yuhan Zhao. I'm one of the faculty members in the HCI group. And today I'm glad to be here to talk about the HCI group and also the research we conduct here at the University of Wisconsin-Madison. So talking about HCI, human-computer interaction, it's different from the conventional computer science because it's really an interdisciplinary field that we study both human and technology. So it intersects with many different fields, including computer science, human factors design, cognitive science, psychology, and so on. That's why you will see we always have collaborations with domain experts and faculty members from many other different departments. And also our research usually have different phases, right? We usually start from understanding the users, the challenges they face and their needs and preferences via empirical studies, including both quantitative and qualitative studies. And then we start to, based on the user's needs, we start to design systems or interactive techniques that is not only effective, but also easy to use, satisfying so that we would fulfill the user's needs. And also our research approach is usually very human-centered. We will iterate our system, our technologies and design with users via multiple different rounds, and also do final evaluations with our target users. So that is basically our research process. And then let me introduce our faculty members in our HCI group. So we have 3 members in the computer science, including Professor Yesol Kim, that you have just hear her talking about her research. And also Professor Bilgin Mulu, who works on human-robot interaction, and also myself working on accessibility and augmented and virtual reality. And in fact, beyond the HCI researchers in the computer science, we also have more HCI folks that is in the School of Computer Data and Information Sciences. And a lot of them are also from the iSchool that covers a way broader scope of HCI research. For example, privacy, health informatics, social computing, and so on. And also campus-wide, as I mentioned, HCI is really multidisciplinary research. That's why we also have many HCI and design researchers across campus from many different departments, not only in computer science, iSchool, but also psychology, education, communication, and so on. So I'm sure that you will get a lot of research and collaboration opportunities here in our university. And now let's switch back, and I want to really focus on our computer science department and introduce each of our faculty members and their research. So I'll start with Professor Bilgin Mulu. He's actually the most senior HCI researcher in our department, and his research focuses on HCI and HRI, which is human-robot interaction. And he leads the People and Robot Lab, and he's been doing seminal research on all kinds of directions around robots. And now I'm going to give you some examples. So one direction that Professor Mutlu has been working on is to design interactive agents to support people in different real life scenarios. For example, robotic, conversational, and also text-based agents. And these agents usually integrate sophisticated language models and also nonverbal interactions. And he has been working on exploring how to enable these agents to support long-term interactions and also adaptation to the user's environments and also their preferences, so that his research really contributing to both the fundamental research and also the applied design directions. And he has also been build design and programming tools to enable users, including both starters and also experts, to program and control their robots. For example, the software tools that support visual programming, demonstration-based programming, and also multimodal and user programming. And in his research, he always integrates formal methods to ensure the correctness and robustness of his system. So in this image, you can see that they're building this graphic-based user interface to support programming with robots. And his research also contribute to the accessibility field that he designed robotic assistive technologies to support people with diverse disabilities. For example, older adults, individuals with cognitive and mental disabilities, as well as their families and caregivers. So his research has been bringing a lot of big impact to the field. And he always involved the real population, real target users in his research and leveraging human-centered approaches. And his research also is very interdisciplinary, so that he would collaborate with different community partners as well as domain experts. So that's the research for Professor Mutlu, and then Professor Yesol Kim, whose research focuses on visualization, accessibility, and data science. And we actually also have some collaboration in terms of the visualization accessibility for people with low vision. So you have heard her give you a very thorough introduction of her work. So I'm just going to briefly show all the cool visualizations that she has been investigated, and won't repeat, all the details. And by the end, I'm also going to introduce my own research. So my research intersects between accessibility, augmented, and virtual reality. I lead the Mad Ability Lab. So that's the little logo of our lab. So in our research lab, my students and I, we really focused on investigating the challenges faced by people with disabilities and try to design and build intelligent interactive systems to enhance human abilities in both their real-world activities, but also the emerging virtual world. So assume many of you may have used different VR devices and heard of the release of the Apple Vision Pro, right? So that's a really blooming area. So I'm going to also give some examples of the research I've been doing in my lab. So first of all, for the real world, like people with disabilities, they face a lot of difficulties in their activities of daily living. And we design and build context-aware systems to enhance their abilities in their daily life across very different activities. For example, shopping, navigation, reading, and so on, right? And then in terms of context, here we refers to both the user's behaviors, their intent, as well as their surrounding environment. So this is one example. We try to use eye tracker to understand people's behaviors, and very specifically a gaze-aware system to support people with low vision in the reading task. And this is a research that we collaborate with the vision science department, Dr. Sambrita Mondel, who's actually a low vision optometrist for specialized in the low vision field. And we use the eye tracker to track, understand, and also model people's gaze behaviors, and specifically the very unique behaviors for people with low vision, and the design technologies that would generate real-time augmentations. For example, this image if you're seeing is that we're trying to recognize people's line switching behaviors, and also when they are hesitating around a difficult word, so that we can generate different augmentations, for example, highlighting and magnification and so on. And another aspect of the context is to leverage the state-of-the-art vision model to recognize the surrounding environment of the users, and then provide different augmentations. And usually we would build AI-powered augmented reality systems to support people. And this example is, again, for people with low vision in the kitchen, where people try to interact with the different kitchen tools. And this is a very complex and even risky task for people. For example, if you want to find and grab this knife very quickly, right? So what we are doing here is we are leveraging different vision models, not only recognize one whole object, but also recognize the affordance, meaning the interactions they would support. For example, which area you can grab and which area is more risky that you really want to avoid. And then we design corresponding augmentations and render them on the AR devices in real time. So this is actually a collaboration with University of Washington. Beyond the real world, we also look into the virtual space since it's a really emerging technology and also it brings in a lot of accessibility issues. For example, the VR environment is very vision dominant, right? So it brings a lot of difficulty for people who are blind and low vision. That's why another line of our research is to design systems and also AR, VR techniques to make these virtual space and interactions more accessible. So this example here is we designed and built a toolkit in VR that provide all these 14 different tools for people with low vision to augment a specific scene. And beyond that, we also design audio-based and haptic-based technologies. For example, a haptic controller that simulate the cane interaction in the virtual space for people with who are blind to navigate the virtual space and so on. And beyond accessibility issues, there could also be social barriers, right? For example, if you have used a social VR, it's very avatar centric, right? And then we face this issue in terms of how we could design suitable avatars to represent different disabilities without introducing new social stigma and misconception, right? And here's another type of work that is relatively qualitative and experimental, where we conduct the studies, for example, interviews, observations, theory studies to understand how the people with different disabilities would prefer to design their avatars and their experience in social VR when they use these avatars. And based on that, we derive design guidelines to inspire more inclusive avatar design and also construct avatar libraries for people with disabilities. So with that, I want to just conclude my presentation today. So that's everything about our HCI group and our work. And we're going to have open house to both the people and the robot lab and also my own Madability lab from 2 to 4 p.m. today. So you're very welcome to join us, see some demos and talk to our students. Thank you so much.
Thank you so much. What an exciting morning so far. We are going to take a break from 10:30 to 10:45, and coming up on the screen very shortly will be a QR code. If you want to grab the schedule for today, we'll have this QR code is kind of around on the tables as well, but just have this up on your phone so you can see when all those open houses are, what's happening this afternoon. So just grab that and check it out. Again, we'll be back in here at 10:45 to continue our presentations. I just want to remind everyone again where the bathrooms are. If you walk out the door straight across, there's a big red wall and elevators. They're over there. There's a men's restroom, women's, and a single stall. So there's also a water filler upper thingy. So go on, take your break. We'll see you back at 10:45. Oh, yes, put that one in your pocket so you don't get confused. So yeah, use this one, and then you can see. So right now, okay, up. So there's for you. Excellent. Yep. Oh, did I turn? Nope, the mic is still on. I think we're ready to get you started then, Ginny, if you're ready. All right, everybody, welcome back. We've got a tight schedule of faculty talks, so we're going to keep rolling. And up next, we have Theory with Professor Jinyi Kai. Thank you.
Thank you. Before you clap, you should have heard me first and see if you like it. So I am today going to speak for my colleagues. Can you hear me over here? It's part two. Okay, all right. So I'm nailed here. Thank you. Okay, first, welcome to UW-Madison. I hope many of you will choose to come here. It's a wonderful place. I would like to speak on behalf of some of my theoretical computer science colleagues. Theory is one area of computer science, and many of you probably have taken some theory courses in your undergraduate study, but I'd like to give you a flavor of what theory is like here in UW-Madison, and maybe it's also some of my personal views of how things are. So let me get started. My name is Jinyi Cai. So what is computer science? Well, as I said, it's an area, but we in theory think this should be all. But just a joke. It's the foundation really of computer science, and if you look back into the history, how computer science was founded, this came from the ideas of Turing, Gödel, Church, and also some of you may or may not know that in the foundational work, Stephen Kleene, who was a well-known logician, and Barclay Rosser, the two of them were actually former colleagues, faculty member here in UW-Madison. So UW-Madison actually had a great tradition in that. It is about what is computation, what resources do you need, how efficient can you do things, can you say things that this absolutely takes that you cannot do better? Theory tends to be very skeptical about claims of optimality unless it's proved. So we take things with very much of a sort of mathematical view. Say, for example, we don't consider NP-complete problems as not solvable. We're just saying that it's conjectured to be not solvable. But then just because it's not solvable, it doesn't mean that it cannot be done in practice for actual instances, and you look for conditions under which special cases and special criteria such as randomization, approximation. And then you can actually talk about under approximation you cannot do, for example. And this will be another level of intractability. So there are actually lots of sub areas of theory, and I myself is in complexity theory, but various people in this department and also around the world work on many different areas. I would probably say that on the first order approximation, you have the complexity theory and algorithms, okay? And these are sort of the two sides of the coin. You want to talk about something you can do efficiently, that's usually the algorithms, and you reason about things you cannot do, which usually is complexity. To say things that you cannot do is not just a negative statement. In fact, it has value. It's like, you go to a bank, you see a big vault, and the fact that the vault is there is to say that you cannot break in. And the fact that you cannot break in has value to you, right? You want things that certain, security is basically predicated on things to say that you cannot do certain things, right? And cryptography, security, learning theory is very popular these days. A lot of interesting questions where you look at input that are influenced by various probabilistic noise and incomplete information. And what you like to say is that, can you get a good sense of things by not even, looking at the whole thing, for example. You want to get a good estimate of something, whether the input comes from a good mixture of Gaussian distribution or things that are noise. Can you weed out the noise? Can adversarially someone add a certain percentage of noise in your data, and yet you can weed the outliers out? You can ask all sorts of interesting questions. Another very up-and-coming area, I guess, is quantum computing. But at the end of the talk, maybe I'll show you something, my personal view of what this thing is. Anyway, as I mentioned, that the emphasis will be on the rigor and things you can prove. I mentioned about the historical roots. But if you look at like the most fundamental contribution to computer science, and if you measure this by, say, what the percentage of Turing Award winners that were in theory, I would say, it's probably the biggest crowd among the theory, among the Turing Award winners. Of course, you're not required to get a Turing Award when you get your PhD. It's just that sort of the taste and the perspective, how you look at things. And we like to get the idea that there's an idealized, what is the aesthetics, what is the beauty, and beauty and truth above all, really, in theory. Here are the list of current faculty in our department who specializes, or mainly specializes in theory. There's Eric Bach, there's me, there's Elias Diakonikoulis, there's Dieter von Melkebeek, there's Professor Samos and Professor Goyo. Although I would unfortunately tell you that Professor Samos has just informed us that he will be joining another university. So in theory, there are high demands. On the other hand, we probably will have more new faculty joining in this year, and also during the time when you are here. So this is just a current snapshot. And he's still officially here, so I put his picture here. We have probably 15 or so students, and they study with various individual advisors, sometimes co-advised, but mainly by one. Once they get their PhD, they go to academia or industry, and these are various different institutions they are currently a member of once they leave here. So I'll just say a few slides for each of the faculty. I only have 15 minutes, so I will be very brief. And every one of you is encouraged to take a look on the website, look for their publication, their CVs, and in university setting, I would say almost all, and especially probably true for theory, that almost all our research is public, in public domain. There's nothing classified here. So you're all welcome to take a look and try to get a sense and talk to individual faculty, get to know their area better. Professor Eric Bach is a world authority on computational number theory. I think his specialty has to do with analytic number theory. For example, he has some of the best work on how to generate predetermined prime distributions of products and things like that. He's also having interest in some public key cryptography, computer algebra, pseudorandom generators. So here are some special topics that he had worked on that I would consider as having a great influence over the years. I don't know how many of you have been exposed to computational number theory. There's a lot of interesting concepts and trends that initiated from areas in computational number theory. For example, randomized algorithms. Now it's pervasive everywhere in computer science, everywhere, right? Randomized. It came from the original idea of that you could actually tell if a number is a prime or not. It's called a primality test. And it was shown that you have a very efficient randomized algorithm before any deterministic ones were found. So randomization, and of course in cryptography, these all come very natively and naturally. I work in complexity theory. You can check on my publications. I guess you just type in, you don't have to remember this link. This is to prove the existence of such a link. So I have been focused on classification problems. You look at the entire class of problems and you want to classify, okay? This is very much like a chemist. You want to have the element table. If you studied in your undergraduate course of NP completeness, people teach you, here's an NP complete problem. Here's in polynomial time. Here's another NP complete problem. Here's another polynomial time. And if you look at the Bible of NP completeness, Gary Johnson's book, there's a thick section toward the end, about 1/3 to about half, that lists hundreds of problems that are NP complete. And but these are still sort of like I don't mean in a negative sense, but it's still very medieval in the sense like you study your masonry from a master mason. You say, here you relate the brick. Here's how you do it. And, instead, this approach is now trying to classify everything. So you just describe your problem in a formal setting, and then this the element table is built for you. Just look industrialized in some sense. So it's summarized in this book, which if you're interested, take a look. It's been published. Let me mention one, sort of one thing new that I just published. For example, I don't know if you can read all the text, but basically it says that factoring problem. So you have a number which is a product two numbers which are primes, and they are hundreds of digits long, let's say. And this problem is basically at the heart of all the security of RSA, and every public key cryptography refers to this as the conjectured problem that you cannot solve in polynomial time. As I told you, that the inability to solve something efficiently has value. That's where it is. Yeah? But there was a beautiful algorithm called the Shor's algorithm that says that if I can have certain quantum operations, then you would be able to do in polynomial time. And this, of course, given rise to the whole point of so-called post-quantum cryptography, which is a new, very active area. The Congress is trying to put in billions of dollars into this. This is, whenever threat to the national security comes along, there are the name of AI and quantum computing, which is based on the idea that Shor's algorithm can break RSA. That's all there is to it. So this theorem says that if you have a little bit of the error in the order of, say, n to the third, you can see, forget about this b for now. It says that if you have a little bit of noise in your quantum gates, and if you think about the reality, just about anything in reality has noise. There's no such a thing as absolute infinite precision. The theorem proves that you cannot factor. So this is I'm sure lots of people hate me for this. Okay, but as I said, this is the whole aesthetics of theory. What is proved is what's proved. It doesn't matter what you think. What is true is true. Okay. The research topic of Ilias Diakonikoulis is mainly in machine learning, connecting with algorithms and theory. And he is interested in high-dimensional statistics. His work is very well known in that area. Some of the most foundational work was done there. Robust statistics, again, if some adversary trying to corrupt the data, can you somehow tolerate? Can your algorithm still look into it and say, look, these are something come from, the adversary. We can read them out. Here are a couple of general areas and topics that he has made great contributions for. And there's a very active research group, not just by him, but in the whole department, the whole university, actually. Some people are not in the department. This is a very much of an area that people look after. Okay, so, and it has a lot of connection with classical statistics, if you will, but the focus is quite different. Here, the samples coming for free almost. You have a deluge of data. And the classical focus on statistics is to sort of, I have 100 samples and they are all taken pains to collect. You go to an island, you pick on this. Now the trick is to design a protocol that uses 100 samples, but not 150. Can you do better with it? What can you do? Okay. But now the game is sort of changed. This fire hose of data thrown at you. You can't even swallow the whole thing. You want to get rid of a lot of it. How are you going to pick and still be able to accomplish your task? Professor van Melkebeek's work is focused on de-randomization, connecting with circuit lower bounds, and there's a connection to kernelization and compression. So we can talk about what's polynomial identity testing. So here's a powerful method of randomization. This doesn't come from his work, but it's known in theory. That say, for example, I want to know if there's a perfect matching graph, and that's difficult. And you put down as a permanent where the xij sits at ij entry if there is an edge. And the permanent is non-zero if and only if, as a polynomial, if and only if you have a perfect match. Now that is a very difficult polynomial to evaluate. That's called a number p complete. But if you were to change your xij so that it becomes the determinant evaluation, then the determinant is easy to evaluate. And if that is a non-zero polynomial, then the permanent is also a non-zero polynomial. So you could sort of randomly test the determinant and see if the thing is zero or not. And if it's non-zero, you already know it's not an identically zero polynomial. So this is, but that's one problem that we don't know how to do deterministically. There's no known deterministic algorithm that can do this. Oh, I will skip for Professor Zamos. Professor Reshab works in cryptography and computer security. He is actually very interested in post-quantum security using lattice and coding theory. This has connections, of course, with numbers, number theory, pseudo-random generator, cryptographic lower bounds. So I don't know if you know these things about zero knowledge proofs, which is sort of saying, if I want to show you that something I know, and yet I don't want you to be able to impersonate me to prove to someone else that you know, right? So here's a special case. Like, for example, I look at X and I know it's a quadratic residue, that X is a square of something. So I know the R such that R square is equal to X mod P. And you should think about those P's are 100 digits long, so you can't exhaustively find. So I know a root, but if I tell you the root, you can compute a square, you can see it is. But then you know something about the root, and you can impersonate me and show someone else that you know that. Okay, so there is a way for me to show you that I know that X is a square without revealing anything about its square root. Okay, and that's called the zero knowledge. So that will be homework for you. By the time when you figure your lunch, you're supposed to answer that question. Yeah? So I have an X, I know an X, I know a root, and I would like to show you that it's a square. And yeah, I'm not going to tell you what the square root is. How can I do it? Can I do it? Is there a possibility to? So he's giving me more things, but I think I'm just going to skip this part. Let me mention that, oh, what happened? This is not, so I do want to show the slides. Hi. Oh yeah, good. So I want to show you that there's a list of courses that are mainly oriented toward theory students. I would mention in particular the two basic undergraduate upper level theory courses, if you have not had chance to be exposed to this in your undergraduate CS major, and the two graduate intro courses that are mainly for people who want to know a little bit more about theory. Okay, so I'll stop here and thank you very much. So how does this work? I just can't. Yeah.
All right, hi everybody. So my name is Tage. It rhymes with page. I am speaking on behalf of the systems group to describe our research. So what is systems research? I know most of you are not going to do research in systems. So what I want to do with this time is mainly just to convince you that systems research is cool. And in order to do that, I first want you to understand what this even is. There are many sub areas of systems research. This includes operating systems, storage, distributed systems, systems for machine learning, system security, and even databases has some overlap with systems. I think a good definition of systems research is a system is whatever makes your computer useful. Okay, so it's the software that makes the hardware that you have, which is a bunch of silicon, useful to a programmer. Designing computer systems is quite different from designing algorithms or doing theory. This is some quotes from Butler Lamson's Hints for Computer System Design. One of the big differences of systems is we have to think pretty hard about what the external interface should be. We have to define it in the first place. That's a lot of systems research. It's complex. If you think about what are all the ways you can interact with Linux, there are many more ways you can interact with Linux compared to, say, a machine learning model where the interface is relatively simple, right? You put some data, you train a machine learning model, and then you can do inference. There's not a whole lot more to it than that. Linux has a whole bunch of APIs, hundreds of them. the system has a lot more internal structure. And what I mean by that is when we design the system, we have to decide how to build it. We have to decide what all the components should be, what their interfaces should look like. We have to decide should we expose them to the user or not, and we have to actually build them and implement them efficiently. And finally, the measure of whether we have succeeded in building a good system is much less clear than if we're designing an algorithm. There are some sort of there's some sort of hard constraints, like it should have good performance. That's something we can go out and measure. It's quantitative. And then there are sort of softer things like, is it easy to program? Is it productive for the user? And then there are other criteria like, is it correct? Systems research has a long history. It actually goes back even before Unix and C to kind of the first operating systems. Unix is an influence on pretty much all subsequent operating systems, and C has been an influence. It lives on to this day as an influence on programming languages. So Unix had to be invented at some point, and Unix created a lot of the concepts that we have even today in how operating systems look and work. So again, I want to emphasize that researchers developed this. Researchers decided what operating systems should look like, and that's what systems researchers are responsible for. Then coming into things that are a little closer to home, distributed file systems is something that a couple of our faculty, Remzi and Andrea, they've done a lot of work on stored systems. This is another thing that systems researchers have contributed a lot to, designing how to develop file systems that run, that can be accessed from multiple computers and that maybe even run on multiple computers. And this is something that even students interact with regularly with our own distributed file system called AFS. Then we have virtualization. This is another big thing that systems research was able to develop. VMware was one of the first to virtualize x86 processors. Actually, a lot of people didn't think that this was possible to do efficiently at the time. And then VMware figured out how to do that. So you'll notice that VMware is a company, and it's not academia. There's a close relationship between academia and industry in systems research, especially. A lot of the people in industry did come from PhD programs, and there is influence in both directions. And Zen is another example of virtualization that came later. So these virtualizations solve this problem of, I have a computer, and if I'm not using my computer right now, nobody else can use it, right? It's kind of doing nothing. Virtualization allows us to run several virtual computers on the same physical computer. And that allows us to better utilize our machines. If you think about something like Google running a whole bunch of workloads on a whole bunch of computers, if they let a computer sit idle, they might be letting thousands of computers sit idle, and this would actually be an enormous cost. Google really would not work without high utilization. It would just be too expensive to run. Going into slightly more modern systems, the Google file system, GFS, was kind of the first very, very large scale distributed file system. And MapReduce was an early example of how do we let programmers use a whole bunch of machines. These are both examples of how we scale up systems to work on many, many machines. That's another big theme in computer systems research today. We've kind of moved beyond one machine to how do we let programmers harness a very large number of compute nodes. If you work in machine learning, this is a big theme of today's machine learning research, machine learning systems research. How do we use a bunch of GPUs? How do we use cluster computing to drive our machine learning workloads? And that kind of is the next set of systems. Spark was another example of putting a bunch of machines in the hands of programmers, letting them use those efficiently. This was quite painful at the time, and it's only gotten better since 2012. And this is another example of the power of systems research, is allowing it makes programmers productive in order to write their applications. A lot of the developments in machine learning have also been spurred by systems work, right? So being able to use a lot of hardware and throw a lot of compute at the problem enables machine learning to work. And at some point along the way, that has to come from systems. So what's new in systems research? What has kind of changed very recently? You can kind of break down systems into, it's what sits between, as I said, it makes our hardware useful. So we often think of systems as sitting in the middle of some stack of there's some hardware that we're trying to make useful, and there's some applications that we want to run. And what's new is that we have both new hardware and we have new applications and workloads that people want to run. So let me talk about the applications first. Machine learning is an obvious example, but even within machine learning, there's things like self-driving cars. That's a new workload that we would want to build systems to support. We have a bunch of sensors, and we have a real-time constraint that the car needs to make decisions rapidly. Augmented and virtual reality are other examples like this, where we have a new workload that has pretty high demands. We need to compute very, very rapidly. We need to produce frames at 90, 120 frames per second. That's a pretty tight constraint. On the flip side, we also have new hardware. So the first example here is non-volatile memory. We have increasing access to very large memories that persist after you store to them, right? So that creates a new programming challenge, a new efficiency challenge of how do we actually make use of all of this power that the hardware is giving us? How do we use machines that have a terabyte of RAM, for example? TPUs and other accelerators, especially for machine learning, but also other accelerators. This is hardware that we can develop. Systems research is what enables people to actually write programs that use all of that extra power, right? Without the right programming support, the TPU doesn't actually end up being that useful to you. So who is the systems group here? So we have 6 faculty that consider themselves to be in systems. Andrea and Remzi have been here for a while. They're mostly known for their work on storage systems. That includes building new storage systems, as well as they and their students have done a lot of analysis of storage systems. They've looked at bugs in file systems in practice. They have this paper called "A File is Not a File" that looked at how files are actually used in real operating systems and applications. So yeah, again, both this analysis and system development, also distributed file systems and distributed storage. Mike Swift has done quite a variety of work. Lately, he's been working on non-volatile memory and making use of that. He has a student who worked on a project to look at how will Linux handle terabyte-sized memories. And an interesting part of this research is that what we didn't want to do is go buy a machine that has a terabyte of RAM, because that's very expensive to do. So the student came up with a very clever way to simulate having a lot more RAM than we actually have access to, at an efficiency of about 1 bit per 4 kilobytes of simulated memory. I give this example because this is a lot of what systems researchers are actually doing in practice, is we come up with these clever tricks. We're doing a lot of programming, and we're maybe analyzing real systems. There's a balance in systems research between how things should work, how we'd like them to work, and actually having to deal with the reality of the world today. And I think that project is a good example of the balance of these two. And what that project actually found is a bunch of bottlenecks in Linux where if we had a terabyte of RAM, some things would become exceptionally slow. Like allocating, you ask for some memory, and it takes 30 seconds. Startup takes minutes. These are things that Linux didn't know, right? Bart has done a bunch of work on system security, including analysis of binary images. Bart actually and his students developed this idea of fuzzing, which is a way of finding bugs in programs, even though you don't know anything about the program. In a completely black box way, you can run a program and find, using randomness, find inputs that make them crash. So they ran this and they found a lot of bugs in Unix utilities. Shiv, who goes by Shiv, has done a bunch of work on systems for machine learning. So these are various systems to be able to support running machine learning workloads at scale. This is pretty crucial to making machine learning scale up. In general, this systems research. This allows us to reduce the cost of training, and also by making things cheaper, we can access bigger models, for example. And then myself, I do work at the intersection of programming languages and systems. So a lot of my work is about building correct systems and showing that they are correct. Ethan talked a little bit about my work earlier in the PL talk. So I'll kind of focus on the other people's research here. Madison has a pretty strong operating systems group. CS Rankings, which has you can quibble about the methodology of CS Rankings, but we do actually rank pretty highly. We have several well-known researchers in operating systems. To give you some sense of what classes look like here, which even if you're not in systems, you might be interested in some of these courses. At the undergrad level, these are classes that you might TA for example. We have an operating systems class that I'm actually teaching now. Our operating systems class serves 300 students at least a semester, which is a pretty large scale for operating systems at a university. We also have both undergrad and grad versions of a big data systems class that Shiv often teaches the grad version of this class that helps you understand all of these systems that allow us to use big data, right? That allow us to actually run big data workloads. We also have an advanced OS and advanced distributed systems class, which should get you exposed to research in these areas, respectively. And you get to do a project in those areas. And then I also teach a special topics class on systems verification, which is very new. This is kind of cutting edge of systems. What do our students do? Here's just kind of a snapshot of some paper titles from primarily student authors across the spectrum of our faculty. So WhiskSort, for example, is a paper that uses non-volatile RAM and tries to make best use of that non-volatile RAM for sorting. MADFS is a way of exposing persistency to an application. So this is an example of a project that actually, I think it works within Linux. So that's another thing that systems researchers are often doing is you take these big systems like Linux and you actually figure out how to use them. That's something that I think is the purvey of systems research is we're not scared to go and say modify Linux or modify some big system. Bagpipe is one of Shiv and his students' papers. This is an example of this developing a system to make a particular machine learning workload work faster, distribute well, for example. Our students go to various places after graduating. We have a few recent academics, Aishwarya and Ram both went to UIUC very recently. And Vijay a little bit earlier graduated from the systems group and is now a professor at UT Austin. Many students in systems also go on to industry. We have a bunch of people at research institutions, VMware Research, now part of Broadcom, and then Facebook and Microsoft within their systems groups doing research, as well as Google and Amazon, which also do a lot of systems research. And then a number of startups. You can see a long list of past students and kind of where they went after graduation at the systems website. I also want to just go through some more specific projects. I already talked about some of these things, but let me just give you a breakdown of what the faculty do. We have a bunch of people working on storage systems, broadly speaking. A lot of Mike Swift's research is using non-volatile memory and these very fast SSDs based on non-volatile memory. This is a big challenge for systems because these things are really fast. And if you don't do some careful work, you don't get the most bang for your buck, right? These things operate at very high speed. But if your application can't keep up with the storage or doesn't use it efficiently, then you don't actually get the value of this very expensive thing you paid for. Remzi and Andrea have worked on storage systems, very recent work on making them more reliable, developing better consistency models. So consistency is kind of a correctness property for the storage system. By providing strong consistency, we can make it easier to program the system. And a lot of the research is on how do we do that while still having reasonable cost, right? The system is going to have some performance. We want the programmer to be able to get high performance, but we also don't want to overly burden them. And I work, I've done in the past, I've done a bunch of work on verified storage systems. So developing file systems, especially that have mathematical guarantees that they do what they're supposed to do all the time. Systems for machine learning is another big area of research that both Shiv and Remzi and Andrea have worked on. A lot of work on distributed machine learning. Most of Shiv's work is on developing systems to support machine learning workloads. There is also the opposite, which is using machine learning to support systems, right? So an example of this is this idea of learned indexes, where we try to use machine learning to decide what is going to go, what indexes a database should have, for example. So Shiv has also done some work on that, and Ramsey and Andrea, but a lot of the work here is systems to support machine learning workloads. There's also a number of projects on distributed systems. Bart has done work on performance profiling. It's not quite distributed systems, but it kind of has some overlap. Then Mike Swift has some research on high performance networking, which is one aspect of making a distributed system efficient. And my current research and kind of near-term research is on verifying various properties of distributed systems. Distributed systems are notoriously difficult to make correct. So this is a big challenge that we address using formula methods that, again, intersects with all of these PL techniques. That's all that's all the technical content that I have. You can meet some systems students in the systems group who work with systems faculty this afternoon at 2 to 3 in 4310. And then there's various one-on-ones with faculty. Thanks, and I'm going to hand it over to Matt to talk about architecture.
Maybe this one works. Okay. So while we get the slides set up here, let me introduce myself. I am Matt Sinclair. I'm one of the computer architecture faculty here. And I'm going to talk to you about all the really cool work that we have been, are continuing to do, and will be doing, past, present, and future. And I think a lot of what you heard Steve talk about in the welcome talk this morning, and a lot of what you just heard Tej talk about a minute ago can be echoed in the architecture talk as well. Before I get into that, though, these are the 6 of us who primarily work in computer architecture: Miko, Karu, Josh, myself, Guri, and Swamit. But as I mentioned, I think it's really interesting to understand the history. You heard Steve talk about how people who worked here, who are now emeritus faculty or continuing to work in some cases, are the people who really built the field of computer architecture and systems and other ones. And that goes all the way back to 1951. This is a real picture of Gene Amdahl's thesis, which was published here at the University of Wisconsin. I apologize that it is not the most aesthetically pleasing picture. That was the best picture I could get of his thesis from 1951. But nonetheless, the point is, we have been doing foundational work here, even predating modern computers existing, looking at how to design those kinds of computers. And that trend has continued in the more recent past, if you will, moving from the 1950s up to the 1970s, where people like Guri Sohi, Jim Smith, Jim Goodman, Mark Hill, and David Wood were in the era of uniprocessors, where every year, as you might know, we were every 2 years, every year, depending on your point of view, we were doubling the number of transistors we could fit in a given piece of area, and we had 34% annual growth without increasing cost or joules. And a lot of the foundational techniques in this space were invented by people and their students here. Fast forward to the more modern day, 2005 through the 2020s, and we entered the multi-core and accelerator area, which is just continuing to be an ongoing transition. And again, faculty here, including some of the faculty who are currently here, have been leading the charge doing that work on how to integrate these different types of processors, how to invent techniques for, say, out-of-order superscalar processing, as well as, especially in Karu's group, looking at what happens when we need to try and power all of those things that we're now connecting together at once. And it turns out that led to this really huge leap forward, which is known as the dark silicon era, which is arguably the era that we're now facing as we come to the point where we just can't power everything on the chip at the same time. And because of that, there's some big questions about the future of computer architecture. And maybe that for those of you who are more focused on machine learning or HCI or other areas, you might wonder, well, how does that affect me? Well, the reason why it affects you is ultimately challenges we're facing as architects, things like the end of Moore's law, have been driving in a very virtuous cycle the innovations in all these other fields. So the way I like to think of it is we have had continuing improvements in transistor scaling from Moore's law and Dennard scaling, which have allowed us to build ever bigger, faster, cheaper, sometimes lower power processors. which have then been fed into algorithms, people like machine learning, who have ravenous appetites to make bigger and bigger systems able to run larger and larger things to solve really important problems. Those algorithms in turn need more and more data. But to feed and run that data in efficient amounts of time, you need increasingly faster, cheaper, bigger, more efficient hardware. So we've had this virtuous cycle that all of those innovations you saw me talk about from 1951 with Jean Amdahl all the way to today have leveraged. But as we're reaching, depending on your point of view, the end of Moore's law, the slowing of Moore's law, or somewhere in between, with these challenges from above, where software, increasingly things like machine learning and others, have ravenous and ever increasing demands for all the different application spaces and more shown there, we have some challenges that, for me, make this a really, really exciting time to be working in architecture, because we're at the point where the workloads need better and better ways to design more efficient architectures, more efficient systems. We have underlying it Swamit, who's next going to tell you how quantum computing is coming bit by bit to help solve some of these problems. But ultimately, for all of you, even if architecture is not ultimately what you go in and work in, hopefully what you take from this talk is that you should really go and thank your nearest computer architect, because they're the ones who are making all those super crazy, super large, ML algorithms like Vikas will tell you about in a few minutes, run efficiently, and so it doesn't take you a year and a half to get that trained ML algorithm back. So why might you want to come here and work with us? You've heard me talk a little bit about this strong history spanning processors, memories, and simulation. If you're familiar, we have been the folks who have not just released, but currently maintain and advanced state-of-the-art tools like Jeep GPU Sim and Gem 5, which are widely used across the community. And I'm on the project management committee for Gem 5, for example. So this is a tradition that started many years ago with tools like Simple Scalar and proudly continues to today. We have a strong present where we're doing really high impact work in a variety of spaces, not just multi-core CPUs, heterogeneous systems, quantum computing, security, transactional memory, and many others. And as you heard Steve talk a bit about this morning, both the people who have done this work and are now emeritus, the current people, and the next generation people like Swamit and myself have gotten a number of awards at different points in their career, including being IEEE ACM Fellows. You've heard Steve talk about the National Academy of Engineering this morning, and even in the case of us younger folks, some SIGARCH TCCA Outstanding Dissertation Awards. And it's not just academic awards. We've also had a number of faculty go on to do chip startups with some really, really cool results that have come out of that. So it's not just the present that's powerful. We've also seen a lot of our students go elsewhere and take the kind of ideas that we've founded here and bring them all over academia, ranging from very big top R1 schools like Illinois, Texas, and Michigan, to including teaching faculty, faculty at more teaching focused schools like Rose-Hulman and everywhere in between. And just like the folks you heard Steve talk about here, basically all of these folks are NSF Career Award winners. 4 of them have won Sloan Research Fellowships, as well as Maurice Wilkes Awards, which are really, really high honors in our community. And very similar to what you heard Tej talk about, I know he just told you that the TPU doesn't matter if we don't have an operating system on top of it. I don't know if I personally agree with that, but nonetheless, that's I think there's some synergy there. Our graduates, in addition to academia, have also gone on to work at essentially every major company, big and small. And maybe to be slightly boastful, I think I can say, basically every processor in the room that you have on your phones, on your tablets, on your smartwatches, et cetera, there's somebody who came through the computer architecture program here who had a role in developing that. And so that extends to the future. We have a lot of top papers appearing at top venues in recent years. And we hope that you'll consider coming and joining us and adding your name to this slide in the future. To briefly cover that research, I know since we're running a bit long, I will let Swamit tell you more about the quantum computing in a moment, but just to cover the rest of them, Miko runs the FARM research group, where he's focused on system and processor design, and this includes a whole bunch of really cool things. One thing I want to highlight in recent years is he's been doing non-von Neumann biologically inspired computing, including bitstream computing, where if you can imagine it, your processor can only process 1 bit at a time. which presents really, really interesting trade-offs about how long something is going to take versus how efficient you can make it. Of course, he's done a bunch of more classic work as well that he's also doing today. Karu's group, he is one of the folks who's gone and done chip startups and come back. And what they're really focusing on is what I would call general purpose accelerators. So how do we design, not like your smartphone where we have about 100 different accelerators today, but how can we narrow that down to like 5 accelerators that are able to do all the different functionality of the work in your smartphone, but with a much smaller area and equivalent performance and efficiency or better. And so there's some really, really cool techniques that his students like Mike Davies are doing in that work right now. Josh runs the Stacks research group, where he is focused on energy-centric computing. In particular, he's been looking at things like energy harvesting, intermittent computing, and approximate computing, ranging the stack from circuits all the way up to the programming languages that you heard Tej talk about a moment ago. I run the HAL research group, where we're focused on heterogeneous systems. And in particular, my group has been looking a lot at when we move into this era where we no longer can design single monolithic dies that hold all of our functionality anymore. How do we start integrating these many smaller chips or chiplets together in reasonable ways? And it turns out you have to rethink basically everything that we thought we knew as architects: data movement, synchronization, scheduling, power management, and a whole range of other problems as we move into that space. And as I mentioned before, I also do a lot of work on leading the community's effort to build and maintain tools, if that's your kind of interest. Guri runs the multi-scalar group, where they are focused on, as he likes to call it, the kind of processor design that helps the 99.999% of people who use computers not just for machine learning. So that includes looking at traditional and non-traditional multi-core architectures and looking at ways to program them efficiently, as well as some ways to make them more secure. And then Swamit, as I mentioned, he is leading our efforts into quantum computing. But since we're running a bit long and Swamit's going to tell you all about that really cool work he's doing, I'll let him tell you more about that in a moment. But just to end, ultimately, as you heard Steve talk about and Tej talk about before, in the architecture group here, have been, and are continuing to do really, really high impact work. We hope you'll come and join us and continue that proud tradition. And if you'd like to meet some of the current students who are driving that work forward, they will be in the set from 3 to 4 p.m. today. If you don't know where the set is, it's essentially directly across the street from where you are right now. So I hope you'll consider joining us and come and chat with us later in the day. Thanks.
Okay. Okay, perfect. Thanks, Matt. Thanks. Tej is probably not here, but I think this is a really nice continuation. We started with systems architecture. Now we are going to talk about quantum computing, and I'll convince you why it's a computer science problem, not just a physics problem. So quantum computers are a type of computers that will use or that uses properties of quantum mechanics to solve really hard computational problems like simulating a molecule or factoring numbers or certain optimization problems that are very hard to solve using conventional computers or even conventional supercomputers, right? And our hope is that by building these new type of computers, we can make headway into these really important problems. And the reason we could solve these problems is because we encode information differently on a quantum computer. Quantum mechanics gives us certain properties that we can leverage to build very efficient algorithms to simulate quantum systems, essentially molecules, materials, and so on, right? So if you think about a classical bit or conventional bit, it's a binary system, right? Whereas if you think about a quantum bit, it's a vector. So with one device, you can represent a vector, manipulate this vector by using quantum operations and so on. So this inherent richness of information helps us solve hard problems very quickly. Right, but not all problems can harness quantum power. At least we don't know how to do that today. But there are there are niche applications such as quantum simulation, factoring, search that can solve that can use these quantum mechanical phenomena, and we can accelerate those problems, right? So if we think about quantum computers, they are not general purpose machines. We should think about quantum computers as accelerators, very similar to what we do with GPUs. Hopefully, we'll be able to use quantum computers to accelerate some of these hard problems. But if you think about quantum computers, it may seem alien, but there are many kind of familiar parts. Like, for example, control electronics that controls quantum bits is made out of FPGAs, right? So if you are a computer engineer or if you're a systems person, you can contribute to building quantum computing, right? One key distinction between quantum accelerator and a conventional accelerator is quantum computers reduce the complexity of the problem, right? You can solve a problem with a significantly better complexity, but at the same time, it adds certain constant factors because it's not very easy to run computation on a quantum computer, right? So as a system architect or as a architect, we think about how do we reduce these constant factors, how do we enable sort of more efficient ways of building quantum computers. And this is not kind of a fiction. There are companies out there building quantum computers. So a couple of years back, Google demonstrated that with 53 qubits, they can run a quantum circuit on their quantum computer in 200 seconds. And if you want to simulate the same, it will probably take thousands of years, right? So there are real hardware platforms out there, and people are trying to understand how we can use these platforms to solve practical problems. One challenge in solving problems is all these systems, quantum systems are extremely fickle. They are sensitive to noise. So whether it's memory or whether it's compute on a quantum computer, you get errors, right? And how do we mitigate these errors? That's one of the most important challenge that people in physics, computer science, and other departments are figuring out, right? So one way we can tackle this problem is by using quantum error correction. Essentially, we use collection of noisy quantum bits to create one fault-tolerant logical qubit, but it's extremely expensive. Expensive both from a qubit device perspective and expensive also from the scale perspective, right? So if we truly want to leverage quantum computers to solve practical problems, we need to build large-scale systems. And there are many companies who are committing to building fault-tolerant quantum computers. So one problem specifically that we focus on is how do we control large number of quantum bits? So for example, this table shows that some numbers for Google's quantum supremacy experiment, where to control 53 qubits, they needed 30 plus FPGAs, very large number of digital to analog converters or DACs. So how do we tame this scaling? It almost scales linearly with growing number of qubits. And to build fault-tolerant quantum computer, we need maybe millions of qubits, right? So how do we think about reducing this overhead? Are there clever architectures? Are there tools that we can build to reduce this complexity? So overall, the community kind of is focusing on this roadmap at a high level. Today, we have these noisy intermediate scale or NISQ quantum computers where we want to mitigate errors by building better hardware, developing some software techniques. In the future, we want to scale these architectures, and at the end, we really want to build like a fault-tolerant quantum computer, and that requires new algorithms, new applications, and even new abstractions, right? So here at Madison, in computer science department, we focus on these top three layers of the stack: quantum algorithms, quantum programming languages, compilers, and quantum architectures. And if we have questions related to, let's say, lower stack, we reach out to our colleagues in physics and electrical engineering departments. Right? So one abstraction in the stack is Quantum Compiler. And I just want to briefly give you an example of how a high-level program can be broken into a low-level pulse representation. And that's something that compiler does, right? You take a high-level, a function written in a high-level programming language, translate it into some form of assembly, and then Quantum Compiler optimizes this assembly code to ultimately generate this pulses, right? So if you think about upper levels of stack, you are actually solving very hard computer science problems. Of course, you need to know a little bit about the physics, but the core problems are CS problems in here, right? And we are all of us, Dieter, Aus, and I, and Rishabh, we are kind of in a superposition state. I am part of a computer architecture group, but today I'm talking about quantum computing. Aus is a part of programming languages group, but he's also interested in sort of doing quantum computing, developing compilers and PL. So all of us have affiliation to other groups, but we kind of focus on top three parts of the stack: algorithms, programming languages, and architecture. Right? And we have really wonderful grad students, and they are very successful. We have had a lot of success in recent years. And we kind of focus on building software tools, simulators, and think about how we can scale fault-tolerant quantum architectures, right? So there is a quantum open house in SET from 2 to 4. If you have questions, reach out to these students and learn more about what we do and so on. Okay, thank you.
Hello, can everybody hear me? All right. So I'm Vikas Singh, and I'm going to introduce the computer vision research that goes on here at Wisconsin. Less code, more images. So let's get started. So the computer vision traditionally has focused on designing methods that mimic human perception. That's been the traditional view. But this definition has expanded because the image measurements that you acquire may not always be geared towards human perception. These could just be measurements of the world, and you might be interested in deriving knowledge from. Or you could be interested in taking the measurements, the images, and doing other fun things with it for applications in art. And so that's the expanded view that you will see being reflected in the research that I cover today. So of course, the traditional pillars are still present. So we want to understand what are the primitives that make up the image, what the image corresponds to, can we partition the image into its components, as well as solving the inverse problem. So the images are a measurement of the world. What can we infer from the scene? What can we infer from the primitives that make up the scene? So these are problems that computer vision researchers really care about. And the applications of these ideas are, the list covered here on this slide is already fairly broad, and this list is growing because computer vision really affects a broad range of applications. And on this slide, you can already see that there are some specific use cases that are not seeking to mimic human perception. So for example, with autonomous driving or applications in agriculture that many faculty here are working on, you're trying to do things at a superhuman level and do things faster, more efficiently and such. There are also applications in medical imaging, doing fun things with art and so on. So as this probably already shows you that if you enjoy a bit of everything and want to work in an interdisciplinary topic, computer vision really provides you a very good opportunity, all the way from covering topics from optimization and probability theory to interacting with physics and optics, as well as, can you design better cameras? Can you design better devices? So computer vision gives you a bit of everything in terms of flexibility. So there's 5 of us who are solely interested in computer vision problems and topics around it. But you should realize that there is a broader adjacent community, folks upstream of us in signal processing, as well as those focusing on applications of computer vision ideas. So the community is quite rich and vibrant. So 5 faculty members, 25 plus students, and there is a very intensive collaboration across many of these groups. So it's a good community which you will enjoy. So what I'll do now is just give you a very quick overview of what various groups are working on. And that should, I think, help you see the high-level picture of what type of topics you might be interested in working in. So Pedro is an assistant professor in ECE and CS. His main research is in self-supervised learning and multimodal learning. And more recently, he's been looking at methods and algorithms that can combine multimodal data for various tasks. And this is especially important in settings where each modality is somewhat weak or lacks a great deal of supervision. So in those cases, by bringing in multiple modalities in a biologically inspired way can lead to powerful new capabilities. More recently, Pedro's group has been focusing on audio. So one question here you could imagine is that, let's say you have a video sequence, how do you learn representations of the image data and the audio data together in a synchronized manner? So this is a topic where his group has a number of interesting results describing how new concept discovery can be enabled. And you can imagine that if you now tie this together with generative models, then you could imagine being able to generate synthetic videos that are automatically synchronized together with audio. And this is a topic that he is very active in, with a number of interesting results over the last couple of years. So Yongjae's work is primarily on designing AI systems that can interpret visual data with minimal human supervision. So he has worked on a number of different topics covering image recognition, image generation, first-person vision. But more recently, his work has been on image generation and multimodal vision and language models. So one of his recent results that's quite popular across the vision and machine learning communities is this multimodal vision language model that can tap into the inherent capabilities of large language models, but also help you deal with visual data. So next is Mohit, and Mohit's interests focus on designing better computational imaging systems, so better cameras and corresponding algorithms for applications in robotics and scientific imaging in general. So one of his recent focuses is on cameras that are very responsive to individual photons. And it turns out that these types of single photon cameras are extremely good at situations that are quite difficult for regular cameras, such as very high speed motion, extremely bad weather, extreme dark environments. So how do you acquire image data under these circumstances and then have algorithms to process that and provide you knowledge? So one of Mohit's lab's broader goals is to develop systems that can operate in extremely challenging environments. So let's say outdoors in dark environments, or extremely strong sunlight, or underground environments. And his hope is that these sorts of systems will give you brand new capabilities in terms of applications in robotics, self-driving cars, and so on. So the next group is Yin's group. His main research focus is on computer vision systems for human behavior analysis. And one of the applications that he is interested in looking at is how that can improve human health. So more recently, he's been looking at video data that comes with narrated text. So what is going on in the video? And one of the questions is how you can use input data of this type to do representation learning that can then be used to provide descriptions of videos. And he's also done a lot of recent work in wearable systems where you can design specialized sensors, as well as the measurements from those sensors can interact together with the image data and provide you brand new capabilities. So this is a picture from a couple of years ago. So my research in my group focuses on use case inspired algorithm design, covering computer vision and machine learning. So just to run through a couple of examples for you. So this was a project focused on designing efficient object detection systems that could run on mobile platforms. And then we realized that some work early on tensor factorization that we had done could be a good starting point. And then eventually this led to new algorithms that are shipped with the TensorFlow object detection API and were popular on a couple of mobile devices that you see there. On a different note, my group has also been quite active in participating in national studies. So this one was focused on preclinical Alzheimer's disease, where data is being acquired at multiple different sites. And the data could come from imaging data, but it could also come from other types of clinical and cognitive data. And then the question is, can we design mechanisms which can harmonize these different types of measurements and provide you statistically rigorous interpretation and guarantees when you use this data for downstream analysis. More recently, we have been playing around a lot with transformer models, again, motivated by a number of different use cases. So for example, one of the ongoing projects is dealing with selfie videos, where you narrate to the video how you're feeling. And the goal is to use this multimodal data over long sequences and get an assessment of your emotional health. On the top, you see another ongoing project dealing with EEG measurements in the context of assessing sleep and its role on various other health-related factors that you can measure. As Matt and Swamit mentioned earlier, there is a lot of interest in tapping into the rich computer architecture group here at Wisconsin. And so we have been doing a lot of work in designing ways in which many of these transformer models can be trained on hybrid compute environments so that it doesn't burn a hole in your pocket. So that's all I had. I hope that gave you a good overview of all that is going on. It's super exciting. And if you have any questions, we will piggyback on the open house in the machine learning group. Many other students will show up there. So feel free to reach out to any of us if you have any questions. Thank you.
Hey, folks. I'm glad to see everyone. I'm definitely going to fall off the stage at some point or another during this talk, but anyway. So I'm going to do the machine learning presentation. My name's Fred Sala. I'm an assistant professor here in the computer sciences department, and I work with the machine learning group. So let's see some of the different research areas. Before jumping into it, let's just zoom out a tiny bit. So within artificial intelligence as a whole here, we can kind of subdivide it, and you've already seen some of these areas. Josiah presented earlier for robotics. I'll do machine learning, and we just finished computer vision with Vikas, and then Yudong will follow with optimization. Oh, at 12:15, not at 12. We have a really large research group for doing artificial intelligence in general. I'm not going to go through every single person's name here, but all of these folks are tackling different problems in AI. Most of the folks on top and a few others are in the CS department, but we also frequently collaborate with folks who are in ECE, in BMI, in statistics, in math, and in a bunch of other areas as well. So we're part of this very rich, very collaborative, large-scale AI research group. In terms of machine learning, so these are the folks who are doing core ML, and there'll be a few more as well, so I'm sure I've forgotten some names. Professor Yudong Chen, who does optimization and machine learning. You'll hear from him in 15 minutes. Professor Elias Diakonikolas, he is in theory, TCS, and machine learning. Professor Yelena Diakonikolas, who is in optimization and machine learning. Professor Josiah Hanna, who is in robotics and reinforcement learning. Kirfi Kandasamy, who is doing machine learning, econ, and game theory. Professor Yang J. Lee, who is in CV and machine learning. Professor Sharon Lee, who is working in out of distribution and deep learning. Professor Yingyu Liang, who is doing deep learning theory. Me, and you'll hear about me, I work on foundation models within ML. Professor Steve Wright, who is optimization in ML. And Professor Jerry Ju, who is kind of core machine learning. All right, so I'll also jump through a few of these faculty highlights. And there'll be much more here. We don't have, unfortunately, time to cover everybody's research interests. But please do reach out to us. We'd love to chat more about the kind of things that we're working on. So I'll start with Professor Yudong, who you'll also hear from. So hopefully I won't steal his thunder too much. But he works on optimization and ML. And he divides this into kind of two parts. One is optimization for machine learning. And of course, many of you folks who've worked with things like deep learning know that training these networks requires a lot of powerful optimization tools. But he also works on kind of the other direction, which is learning how to build better optimizers. In the first kind of direction, it's a really big challenge because machine learning has some really challenging optimization problems as part of them. But despite how difficult these problems is, there's a lot of cause for optimism too. So a lot of these challenging problems can often be approximated with easier ones. They can often have this underlying hidden structure that you can expose that make these problems tractable. And often just composing or chaining some simple algorithms can make things work really well. And Professor Chen has done a lot of work in this direction. But then the other direction where you flip it is also super interesting. You can think about the way to learn a better optimizer. And if you do this, you can figure out exactly how to make reinforcement learning really work. And finally, the big question that he's working on is, how do you relate the characteristics and structures of problems to the limits of the techniques that you can do in optimization? So a lot of fun stuff that you'll hear a bit more from in a few minutes. Professor Josiah Hanna, who spoke this morning, works on building learning agents. And his goal in general is to build autonomous agents like robots that can take actions to perform particular goals. And this is kind of a classic problem for reinforcement learning. What Josiah is interested in is not just making this work in simulations or in the lab, but being able to tackle really complex real-world problems, including things like autonomous driving. And in a lot of these situations, you can't just rely on a single agent. You have to have multiple agents performing many different tasks, and that requires a lot of complexity and kind of coordination for them as well. And all of this gets applied to robot learning. Josiah has a bunch of really cute robots. I hope you get a chance to visit his lab and see them play soccer and do all these other kind of fun things. Professor Kirfi Kandasamy is working on a lot of machine learning related to game theory and economics, which is a really exciting new area. And that means he's using a lot of tools like bandits, online learning, and other kind of fun parts of machine learning. The basic motivation for a lot of his work is that the kind of decisions that are made by AI algorithms that drive kind of the economic space, they affect people, but they also learn from people. So there's some really interesting kind of feedback loops that are going on. And two of the examples that he really works on a lot are things like e-commerce, right? So almost everything that we purchase, we do it online now, and it's offered at a certain price by some algorithm. And it's actually very difficult to design an approach that's going to maximize what users want and what they do when they buy, but also maximize revenues for the vendors themselves. So doing this kind of matching is a big challenge, and Kerfy's made a bunch of really cool contributions to it. Another awesome application is for sharing and trading data. So a lot of people will say that data is like the new oil. It's a really valuable thing that we use. And the challenge there is, if we want to share data in some reasonable way, while also making sure that we don't kind of lose our competitive advantage, how do we do that efficiently? So these are just a couple of the cool application areas that Kerfy's work applies to. But also in addition to that, things like resource sharing for cloud compute, social media, and other areas too. All right, for Professor Sharon Lee, she works on reliable open world learning. And the basic idea here is that a lot of the advances in machine learning, we essentially train a model in a lab under some set of assumptions, and then we hope that we can operate well under that set of assumptions. But that's not really valuable for when we deploy our models in the real world. In the real world, we're going to have all kinds of crazy out-of-distribution cases, and we still want our models to be robust to those scenarios as well. So Sharon's work is about making this happen. And to do that, she has a bunch of tools, and she's built a lot of advances in deep learning. So things like uncertainty estimation, out-of-distribution detection, being more robust to all kinds of changes in your data, making sure that you can still generalize in very far from out-of-distribution scenarios. And then things like for critical application areas like healthcare, making sure that you can actually have models that are aware of their uncertainty so they don't do anything crazy. She's also more recently working on things like alignment in large language models. So making these really powerful models like ChatGPT provide reasonable outputs and not allowing them to get attacked either. So for Professor Yingyu Liang, he's working on the theory of deep learning. And the big challenge here is that even though deep learning has gotten very popular, we haven't really had a completely satisfying theory that explains when it works, where it works, and the exact conditions for how it's going to be successful. So how is it possible that these giant deep neural networks that are often super over-parametrized can still actually generalize and can still perform well on new data points? So Yingyu has made a bunch of contributions here. And the really fun part about this is once you learn what's the theoretical underpinnings for these models, you can actually build much more robust models. So here's a quick example. And some of you folks may have seen these kinds of adversarial examples. This is an image of a flower that we just kind of see naturally here. And what the model sees often is something very different. You can kind of see some of it with this saliency map. You can kind of see that it's detecting some of the flower, but it sees it in a different way. And what's happened here is that some amount of noise has gotten added. This is this idea of a perturbation. And for us visually, it doesn't really look any different. This flower and this flower, they look the same. But for the model, it actually really screws up what it's seen. The cool thing is, if you understand what these models are really doing, you can modify their training in such a way that you can first detect things much better. So right now, the model's seeing it way better than before, but it's also robust to these kinds of adversarial perturbations as well. So this kind of work is something that Yingyu's group does as well. Okay, just so I don't run out of time, I'm next. A lot of my work is in foundation models, which include these kinds of large language models, large pre-trained models, and so forth. And a lot of what I do is data efficient learning and adaptation for these models. The basic motivation is that if you follow the story of the companies that build these models, like Google and OpenAI, they blow through like $1 billion on these things. And we can't really replicate that ourselves. I mean, if some of you folks can, let me know. I've got some projects for you to potentially run. But in general, we just don't have the resources to do the same kind of thing. My work focuses on trying to understand how we can use and how we can rebuild these kinds of models with much more reduced kind of costs. So for that, for one, we try to build very efficient model adaptation tools. Take your large language models, make them work on your own tasks in a very cheap way. Another component is getting cheap data. So it's really important to get high quality data to modify these models. And that can be expensive. We don't want people to manually label a lot of the data. So our tools can acquire and cheaply annotate data. And then finally, something I work on, and that's why I have this kind of distracting picture over here, even though we think of these models as running a lot of linear algebra, they actually have some kind of secret covert geometric behavior. And it turns out that this geometric stuff is often a bottleneck for how well these models perform. So I work on making models operate in some weirder geometric spaces, which can kind of give them a lot better performance. This is a tree being learned in this space called hyperbolic space. If you want to know more about this, come and chat with me. All right, so for our next highlight, it's Professor Jerry Zhu. He's actually worked on 20 different areas of machine learning. We're only going to highlight one here. So one thing that he's very interested in is how you can teach models. And this is actually a little bit different from conventional machine learning. We're not going to feed a model 1 million data points and let it kind of figure out what's going on there. We want to target the data that's going to teach it exactly what it needs to know at this stage. And this is much closer to human learning. Like, you guys don't learn from millions of examples. You just need a few. So this is actually getting also closer to traditional control problems. You have kind of a dynamical system, this kind of feedback loop that lets you figure out exactly what's the right data point to make the model continue performing well or to make it better. And he's applied a lot of this work to kind of decision-making problems. So in RL or bandits, to kind of very interesting inverse problems where rather than getting a data set and training a model on it, you try to design a data set that's going to maximize the model's performance. And then finally, to figure out how to get people to behave in a more reliable and trustworthy way, both for models and humans. I'll also highlight Junji Hu, who's working in natural language processing. He has a very broad set of interests. So he's working on all these fun problems. So LLMs, which often make up facts about the world, they can do this thing called hallucination. He's working on ways to make them reliably reason when it comes to knowledge that they may not have access to. He works on multimodal and multilingual models, on trying to evaluate and interpret these models, which is a major challenge since they're huge and difficult to work with, and also on building agents that are built from LLMs that can actually do a lot of our more annoying tasks. And just a couple of examples. For example, he works on these kind of multimodal systems where you can provide a picture and ask a model to describe what's going on and to kind of get similar examples. He works on building agents that can take on different personas and therefore can behave the way you'd like them to. And then finally, he works a lot on combining large language models with these classical tools called knowledge graphs that store information. And that way you can get these models to actually reliably reason and kind of look up correct facts instead of making them up. Before I completely run out of time, we also collaborate with all of our sister departments, ECE, BMI, math, statistics, actually physics, and a bunch of other departments as well. And I'll very briefly highlight some of our collaborators' work. Professor Dimitris Papailopoulos, he works on large-scale efficient machine learning, and also more recently on the theoretical underpinnings of foundation models. Professor Rob Nowak has worked on also many, many areas, but one of his favorites is active learning. So rather than having a model get trained on data just arbitrarily, you can have that model ask, hey, I need some help, I need some information to improve myself. And by doing this, you can train models much faster and much cheaper. One of my collaborators, Professor Ramya Vinayak, works on actually a bunch of different areas, but she's super interested in systems that work with human information and input, but still offer reliability guarantees. So some of the applications that she's worked on for this are things like preference and representation learning, automatically labeling data, clustering and crowdsourcing, and a bunch of other fun areas too. Also, Professor Kang-Wook Lee's group, who studies a bunch of theoretical aspects of modern powerful machine learning models. So things like the diffusion models that are producing images, large language models, and a bunch of other tools. They've done a lot of really fun work. And just very briefly, some of the folks from BMI that we also chat with, Professor Tony Gitter, who kind of works on biological networks more broadly, Professor Sushmita Roy, who works on gene regulation, Professor Colin Dewey, who does combinatorial optimization, and Professor Mark Craven, who is working on a bunch of areas, but including disease prediction with ML. So just a very, very brief kind of summary of all the folks that we work with. One other thing that we want to highlight is that we have this weekly seminar called Silo. We invite folks from the whole country, kind of cutting edge machine learning researchers, and we all get together weekly and chat with them, see their newest work, and we also collaborate as a group as part of this kind of thing. And finally, I know it's a really rainy day, so it's not, showing Madison necessarily at its nicest, but here's some pictures that we took back in 2020. This is what it looks like in summer and kind of at the beginning of fall as well. So, picture yourself on Lake Mendota at that time. Don't think too much about the rainy days like today. Okay, I'll stop there, and I'm looking forward to seeing everyone during the one-on-ones later today.
I just counted, this is the 15th research group talk this morning. But just the fact that we have 15 different research groups shows how diverse and vibrant the research is in our department. And I'm Yudong Chen, and as you just saw, I'm in both the optimization and machine learning groups. But today I'm going to wear my optimizer's hat and tell you how a little bit about the optimization group in our department and why optimization is at least as useful and as interesting as machine learning. Right, so just a little bit about what is optimization. So in optimization, you want to maximize some objective function or minimize some objective function. And when you maximize, you think of maximizing good stuff like profit or reward or the gain or the accuracy, the probability of success. And when you minimize something, you think about minimizing bad stuff like penalty or cost or the probability of failure. Usually you have some kind of constraints such that, for example, probabilities must be non-zero or sum up to 1, or your model must obey certain criteria. So as formulated in this way, optimization is an incredibly general problem. I would say virtually any decision-making problems can be formulated as an optimization problem. For example, scheduling an event like this is an optimization problem. You want to minimize, for example, the probability of conflicts between different events, subject to the availability of rooms on campus. And you choosing a grad school is also an optimization problem. You want to maximize the probability of working on a project you like, working with a professor you like, subject to financial or geographical or familiar constraints. And by the way, UW-Madison is a near optimal solution, if not the optimal solution. And of course, just the fact that you can write something as an optimization problem doesn't mean you can solve it. So what optimizers like me is doing is trying to identify problems that can be solved efficiently, try to develop algorithms that efficiently solve these algorithms, and try to understand the limits of what can be done and what cannot be done. And in this way, optimization is incredibly useful. I'll tell you a bit about the applications, but mathematically, it's also incredibly beautiful. We are getting inspired by the nature, by different fields. And just one of my very recent, as an example, one of my very recent project is on causal inference, which is a problem in statistics. And we want to find the optimal method for doing causal inference. Somehow, the optimal method is given by electrical flows, which a priori has nothing to do with statistics. So there are many beautiful connections like this. All right. And of course, these days, optimization is very closely connected to machine learning and data science. The fact that I am in both groups shows that how close the connection is. And if you work on machine learning, you will have to solve some optimization problem at some point. In general, in machine learning or in data science, you want to find a model that explains your data. So you want to maximize. You want a model to be simple. You want to find the simplest explanations. But you also want your model to sufficiently agree with the data. So this is an optimization problem that can be instantiated in many different ways. And the role of optimization is becoming more and more crucial today because we are using larger and larger models in data science, in machine learning. There are harder and harder problems that we need to solve. For example, since the models are becoming larger, we want algorithms that run fast. So we look at gradient methods, stochastic gradient methods that have a low per iteration complexity. The data is random, it's noisy, so we need methods that can deal with this kind of stochasticity. We need acceleration to make it run faster. We often deal with matrices because many models are naturally parameterized by matrix. There are more problems where we have additional structures such that specific algorithms like coordinate descent or alternate direction will be much more efficient than a naive gradient descent algorithm.
So this is a very vibrant field. It's still developing. A lot of exciting research is going on. There are books written on it. I'm probably going to skip this slide that tells you how to formulate a machine learning problem as an optimization problem, but I think most of you already know this, that I want to develop a model that takes as input some feature vectors. I want to predict the labels. Think about this, the left-hand side is the pixels on an image. You want to predict what the label is. Is it a dog? Is it a cat? And you can write this as an optimization problem where you want to maximize the goodness of fit of your model. You maximize the prediction accuracy subject to the constraint that your model is either linear or sparse, etc. And a prime example of this kind of problem is training a neural network, which of course is a highly complicated, non-convex, non-linear optimization problem. And nevertheless, in many cases, we find that very simple algorithms like gradient descent works well, even when the problem is very complicated. And in gradient descent, you just go downhill. And I think to me, it's still a mystery and a miracle that algorithms as simple as this works very well for problems like training a neural network. And I think it's fair to say that this is still an open problem why it works so well. All right, so let me tell you a little bit about the optimization group and the activities related to optimization on campus. So optimizers and the optimization group plays a very important role in many of the data science and machine learning initiative on campus. For example, we have this high-profile initiative, which is called Institute for Foundation of Data Science, which is an institute led by Steve Wright, my colleague in optimization, funded by NSF. It involved many people across the campus from both CS, ECE, and other departments. There are many postdocs and grad students that are supported by this institute. And we also have partnership with other universities like the other UW, Santa Cruz, and Chicago. And we also have the Data Science Hub, which is led by Michael Ferris, my other colleague in optimization. And just give you a highlight. COVID seems like something in the past, but during the COVID day, one thing that Michael Ferris, my colleague, did is to develop this model that tells you how to efficiently allocate vaccines to different destinations. And it's actually used by the Department of Health Service and the National Guard, and it plays a very important role in how medicine and UW Medicine handling the COVID. So it's very useful. All right, and let me tell you a little bit about the optimization group here. So we have 8 faculty members that we consider the core members of the optimization group. 4 of us is from CS. We also have 3 colleagues from ISYE, Industrial and System Engineering, and another colleague from ECE. So let me briefly tell you a little bit what each of us does. And by the way, many of us like to hang out in this building, the Discovery building, but maybe next year we will all move to the new CS building. All right, so Michael Ferris, he's interested in optimization problems that involve multiple agents. So this includes many problems from game theory, multi-person games. This includes decentralized control where there are different components of your system interacting with each other, trying to jointly optimize the same objective. He's also particularly interested in applications that involve energy system or environmental problems, and also stochastic optimization problems where you need to make decisions sequentially. Steve Wright is our expert in nonlinear continuous optimization. He is an expert in developing algorithms for continuous optimization, analyzing numerical algorithms. He's also one of the pioneers who bring together the data science and machine learning community. So these days, it seems very natural that these 2 communities are together, but 20 years ago, these are two separate communities. And Steve Wright, I think it's fair to say, it's one of the first few people who try to bring together these two communities. Yelena, she is interested in problems that involve trying to both minimizing a function and maximizing the same function over a different variable. So this is so-called min-max problem. And this kind of problem arises in game theory, arises in trailing GANs. And she's interested in many problems that involve finding a settle point of a min-max problem. She's interested in viewing optimization algorithms like gradient descent as dynamical systems and use tools from control theory and dynamical systems to analyze their behavior. And of course, she's also interested in applications in data science and machine learning and working with lower bounds. So this is the kind of problems that tells you what is the best a optimization algorithm can do. Is interested in problems that are connected to statistics or applied probability. So I work on problems that non-convex problems that arise in statistical machine learning, in particular problems that involve a matrix variable. And more recently, I am interested in reinforcement learning, which is a sequential decision making problem for which optimization plays a main role. And one of the general fundamental problem that I'm interested in is this trade-off between optimization considerations and statistical considerations, meaning that for some problems, in order to have a fast algorithms, you might want to sacrifice some statistical accuracy and vice versa. And I would want to understand to what extent this kind of trade-off is necessary. Jeff Linderoth is our colleague from ISYE, so he's an expert in discrete optimization and integer programming. So these are hard optimization problems over discrete variables. Jim Lukey is also from ISYE. He's also interested in discrete and integer programs, and in addition, stochastic optimization. And both of them are interested in the applications of optimization in operation research type problems, including production, scheduling, energy system. So optimization is useful well beyond data science and machine learning. Alberto, who is also from ISYE, is interested in integer programming and this class of optimization problem called polynomial optimization, and which has a lot of interesting applications in feature selection in machine learning. And last but not least, Rob Lowat, who is our colleague from ECE. He works on 20 different problems in areas in machine learning and optimization. But probably because of his ECE background, he is particularly interested in problems that are connected to information theory and signal processing. Many optimization courses we offer. I won't go through them, but I just want to say optimization is very useful, very beautiful, very interesting. It's closely connected to machine learning, but it has applications not just in machine learning, but in many other areas. And so I encourage you to come to our open houses. You will see the optimization students hanging around in the machine learning open house and the theory open house. And we would love to see you there and tell you more about the optimization group. All right, thank you.
Two things. The shelf is in the computer sciences building. If you go from where you're staying in the hotel and walk across to our building, go straight in the door, and the shelf is kind of above the entrance. So this afternoon, our student ACM is going to be having kind of a afternoon TGIF. Thank goodness it's Friday, and there'll be snacks and You can meet with people in between your open houses and your faculty meetings. You can just hang out with some of the current grad students. Okay, the set is across the street. It happens to be in the Union South. It's the big place where you get burgers and beer and stuff like that. So that's where the open houses for architecture and quantum computing will be tomorrow. If you haven't looked at it, there's a kind of an accordion pull down at the bottom that has all the open houses this afternoon. We really got a good response from the students, the grad students for open houses. So by my last count, there's 11 different open houses that you can attend again in between your faculty meetings. Also, unless you're independently wealthy, you might be interested in going to the research assistantship information that Cindy Fendrick is going to present at 4 p.m. That's in 1240 CS, which is our big kind of lecture room on the first floor. Happy hour is at 5:30 at Fluno. There'll be hors d'oeuvres and drinks. And then after that, it will be followed by dinner. We're expecting to have some faculty attending dinner as well, so it's a good time to talk. We'll also have a returning alumni, Nick Kidd, who'll be speaking. And the keynote will be by Professor Young J. Lee, who is an excellent teacher and lecturer. So I'm looking forward to his keynote tonight. On your way out, if you want to grab some swag, it's still over on the table over there. So as you're going out, we'll pack it up after you're out of here. Anybody that, when they registered, signed up for the Woman and Non-Binary Breakfast, you should have received from me an email yesterday with the details. If you did not, please get in touch with me during lunch or this afternoon. Molly and I can be found in the 4th floor of Tower 2 this afternoon if you want to come by and chat about any questions you might have that are administrative. Molly asked me to remind everybody, daylight savings time starts in the middle of the night tonight. So the schedule for tomorrow, you want to be sure that you, are there in plenty of time. Saturday? That's what I thought. Oh, it starts on Sunday. I was like, what? Okay, correction, it is Sunday. That's what I thought. I misheard what she said about reminding about daylight savings time. So no worries tonight. You have plenty of sleep. I think that's it. If you have any questions, we'll be around during lunch, and some other faculty are joining us. If you have space at your table for a faculty, or you guys kind of want to do musical chairs and find other students to talk to, so there can be faculty at the table, so that would be great. Okay. And I'd also like to thank all the people that joined us online for the morning talks. Everybody have a great rest of your day.